Hello there, and welcome to Science for Sleep, where curiosity gets comfortable and big ideas are allowed to slow down. This is a place for winding thoughts, gentle explanations, and science told at a pace that doesn't rush you anywhere. Tonight, we're setting aside urgency, deadlines, and notifications, and instead letting our attention drift outward, far beyond the everyday, towards something vast and quietly unsettling. Because not long ago, humanity built a new way to look into space. Not just a better telescope, but a different kind of eye altogether. One designed to see things that were never meant to be obvious. And when it finally opened that eye, it didn't just show us more stars or prettier pictures, it showed us something unexpected. Something that made astronomers pause, recalculate, and ask whether we truly understand how big the universe is, or even how it behaves at its edges. This is the story of what happens when you look too far on purpose. The James Webb Space Telescope wasn't designed to chase surprises, but it has a way of finding them anyway. It was built to observe faint light, ancient light that has been travelling for billions of years before finally brushing against a golden mirror floating far from Earth. And in doing so, it began to reveal galaxies that seemed too old, too large, and too well formed for where they were supposed to be in the timeline of the universe. That raised eyebrows, then questions, then quiet concern. Because when observations don't match expectations, it's rarely the universe that's mistaken. Before we go any further, let me ask you something gently, without any urgency attached. Where are you listening from right now? Maybe you're in bed with the lights already dimmed. Maybe there's a window nearby reflecting the night back at you. Or perhaps you're somewhere else entirely, with the day just beginning or already slipping away. And what time is it where you are? Not because the number matters, but because this story is about time as much as it is about space. If you find this kind of slow exploration calming, or if it helps your thoughts loosen their grip a little, consider liking the video or subscribing to the channel. It helps this quiet corner reach others who might need a place to rest their attention. No rush. That can always wait until later. For now, let's ease into the story itself. For most of human history, the universe felt manageable. Vast, yes, but structured. The night sky appeared as a dome sprinkled with stars, steady and dependable. Even after telescopes came along and revealed galaxies beyond our own, there was still a sense that the universe, however large, followed rules we were gradually uncovering. Distances could be measured, ages could be estimated. The expansion of space could be described with equations neat enough to fit on a chalkboard. The universe had a shape, a size, and a history that made sense, or so it seemed. When Edwin Hubble discovered in the 1920s that galaxies were moving away from us, and that the farther they were, the faster they receded, it introduced the idea that the universe was expanding, not exploding outward from a centre, but stretching everywhere at once, like dots on a balloon drifting apart as the balloon inflates. This was strange, but it was consistent, and consistency is comforting. Over time, astronomers refined this picture. They calculated the age of the universe. They mapped the distribution of galaxies. They studied the cosmic microwave background, the faint afterglow of the early universe, still visible in every direction. Each new measurement tightened the story. Then, near the end of the 20th century, another surprise arrived. The expansion of the universe wasn't slowing down, as gravity should have demanded. It was speeding up. Something was pushing space apart more forcefully as time went on. That something was given a name: dark energy. Not because it was understood, but because it wasn't. Even then, the universe still felt measurable, mysterious, but within reach. The James Webb Space Telescope entered this story as the next logical step. Hubble, the telescope, had shown us galaxies forming, stars being born, and light travelling across incomprehensible distances. But Webb was designed to go further back, to see earlier, to detect infrared light stretched by cosmic expansion until it slipped beyond what Hubble could observe. In simple terms, Webb was meant to look at the universe's childhood, When light travels across expanding space, its wavelength stretches. Visible light becomes infrared. The farther it travels, the more stretched it becomes. That means the earliest galaxies, the first ones to ignite after the universe cooled enough for stars to form, would be nearly invisible unless you knew exactly how to look for them. Webb knew. When it began sending back data, astronomers expected to see faint, irregular smudges, small galaxies just beginning to assemble, structures still figuring out how to exist. What they found instead were galaxies that looked mature, organized, massive, brighter than expected. These galaxies appeared at times when, according to existing models, they shouldn't have had enough time to grow that large. This wasn't a single oddity. It happened again and again. Quietly, researchers began double-checking their assumptions. Were distances calculated correctly? Were brightness estimates off? Was the mass being inferred properly? Each question led back to the same unsettling possibility. Maybe the universe is larger, or older, or structured differently than we thought. Or maybe all three. To understand why this matters, it helps to consider how astronomers define the size of the universe in the first place. It's not as simple as measuring from one end to another. The universe doesn't have edges you can point to. There's no wall where space stops. Instead, scientists talk about observable limits. The observable universe is defined by how far light has had time to travel since the beginning. Because the universe is about 13.8 billion years old, you might expect the observable universe to have a radius of 13.8 billion light years. But expansion complicates that picture. Space itself has been stretching the entire time the light was travelling. As a result, the observable universe has a radius of about 46 billion light years. Already that number feels unintuitive. Beyond that boundary, there may be more universe. Probably is. But light from those regions hasn't reached us yet, and may never do so if expansion continues accelerating. In that sense, the observable universe is not the universe. It's just the part we can see. James Webb started revealing structures near the farthest reaches of this observable boundary. When those structures didn't behave as expected, it forced astronomers to revisit how confident they were about where that boundary truly lies, and what assumptions are baked into the models that describe it. Some of the tension comes from how distances are measured. Astronomers rely on a cosmic distance ladder, a series of overlapping methods that estimate distance using different types of objects. Nearby stars can be measured using parallax, slight shifts in position as Earth orbits the Sun. Farther away, certain stars with predictable brightness patterns serve as markers. Even farther still, entire galaxies become reference points. Each step depends on the accuracy of the previous one. If one rung of the ladder is off, everything above it shifts. James Webb doesn't just observe light, it observes how that light has changed. Its sensitivity allows astronomers to estimate redshift with unprecedented precision. Redshift tells us how much the universe has expanded since the light was emitted. That expansion, combined with models of cosmic history, tells us how far away and how long ago the source is. When Webb started finding high redshift galaxies that were unexpectedly bright and complex, it suggested that either galaxies form faster than we thought, or distances are greater than assumed, or our understanding of early cosmic conditions needs revision. None of those options are trivial. If galaxies formed faster, it means physics behaved differently in the early universe. If distances are greater, it means the observable universe might be larger than current estimates. And if the underlying assumptions about expansion are incomplete, it touches the deepest foundations of cosmology. At this point, it's worth pausing for a moment and noticing how this information lands. There's no urgency here. No need to resolve anything tonight. Just the awareness that the universe, even when studied carefully, still holds the ability to surprise us in quiet ways. Webb didn't shatter cosmology overnight. What it did was introduce tension. And tension, in science, is where progress begins. As researchers continue analysing data, Some initial interpretations may soften. Some early galaxies might turn out to be closer than first thought. Others may indeed force revisions. Science is patient like that. It doesn't rush to conclusions, even when headlines do. What remains clear is that our picture of the universe's size is not as settled as it once seemed. Not because we were careless, but because the universe is subtle, and each new way of looking reveals layers that weren't visible before. This realization gently shifts perspective. If the universe is larger than we thought, not just in scale but in complexity, then our place within it becomes both smaller and more remarkable. Smaller in physical terms, yes, but remarkable in the sense that we are capable of noticing. A species on a small planet orbiting an average star builds an instrument that floats beyond the moon's orbit and opens a window onto the universe's earlier structures. And then, calmly, it admits that the view raises more questions than answers. There's something grounding about that. For now, it's enough to rest with the idea that looking far enough doesn't just show us distant objects. It shows us the edges of our understanding, and those edges, like the universe itself, have a habit of expanding quietly when observed. Long before anyone thought about mirrors folded like origami or telescopes drifting far beyond the moon, humans were already trying to see farther than their eyes would allow. It didn't begin with laboratories or funding proposals. It began with squinting into the dark and wondering whether the faint points overhead were fixed, reachable, or trying to tell us something. There is a persistent impulse in us to extend our sight, to overcome the limits imposed by biology, atmosphere, and distance. That impulse hasn't faded with time. If anything, it has grown stronger the more we learn about how much lies beyond immediate perception. At first, the universe seemed close. The stars felt like decorations pinned to a nearby sky, arranged for navigation or storytelling rather than investigation. Even when early astronomers realized that planets wandered differently from stars, the scale still felt manageable. The heavens were complex, but not unreachable. Then telescopes arrived, and suddenly the sky was no longer a surface. It became a depth. Galileo's telescope was small by modern standards, little more than a tube with simple lenses, yet it shattered the idea that human eyesight was sufficient. Craters appeared on the moon, moons appeared around Jupiter. The Milky Way dissolved into countless individual stars. Each improvement in magnification didn't just add detail, it added distance. The universe expanded not physically but mentally. From that moment onward, astronomy became inseparable from technology. Every major leap in understanding followed an improvement in how we gathered light. Bigger lenses, better mirrors, sharper focus, more stable mounts, and eventually new kinds of detectors capable of seeing beyond the narrow slice of light visible to human eyes. The reason this process never stops is simple. Light carries information, but it arrives weakened, distorted, and delayed. The farther it travels, the more it spreads out. By the time it reaches Earth from distant galaxies, it is unimaginably faint. Catching that light requires collecting as much of it as possible and protecting it from interference. Earth itself is one of the biggest sources of that interference. The atmosphere bends light, blurs detail, and absorbs entire wavelengths. It shimmers and shifts, making stars twinkle but telescopes struggle. For centuries, astronomers worked around this limitation, building observatories on mountaintops and in deserts, chasing thinner air and steadier skies. These efforts helped, but they could never fully remove the problem. That realization planted a quiet idea that took decades to mature. If the atmosphere is the obstacle, then perhaps the telescope should leave it behind. Space-based telescopes were not immediately obvious solutions. They were expensive, fragile, and difficult to maintain. Yet the promise was irresistible. Above the atmosphere, light arrives undisturbed, images sharpen, faint signals survive. Entire regions of the electromagnetic spectrum open up. The Hubble Space Telescope became the clearest proof of that promise. When it finally began operating correctly, it transformed astronomy. Galaxies multiplied. Nebulae revealed intricate structure. Distant supernovae helped uncover the accelerating expansion of the universe. Hubble did not merely add clarity, it changed what questions astronomers felt confident asking. Still, Hubble had limits. Its mirror, while large for its time, could only collect so much light. Its instruments were optimized for visible and ultraviolet wavelengths, and perhaps most importantly, it could only see so far back in time before the universe faded into darkness. The early universe does not shine in visible light anymore. The first stars and galaxies emitted energetic radiation, but as space expanded, that light stretched. Over billions of years, it slipped out of the visible range and into infrared. To see it, you need a telescope designed not just to be large, but to be cold, precise, and sensitive to wavelengths our eyes will never detect. This is where the idea of building bigger eyes takes on a slightly different meaning. Bigger does not only refer to physical size, it refers to capability, sensitivity, range, stability, the ability to gather faint ancient light without drowning it in noise. James Webb was built for this purpose. Its mirror spans over 6 meters, far larger than Hubble's. But more importantly, it operates primarily in infrared. To do that effectively, it must remain extremely cold. Heat creates infrared radiation, and even a warm telescope would blind itself. That's why Webb carries a massive sun shield, keeping its instruments in deep shadow while it observes. The complexity of this design reflects a broader truth about astronomy. Every time we push deeper into the universe, we encounter conditions that require new solutions. Seeing farther back in time means detecting fainter signals. Detecting fainter signals means reducing noise. Reducing noise means controlling temperature, vibration, and interference at levels that feel almost unreasonable. Yet we persist. Part of the reason is scientific curiosity. Each increase in observational power has historically revealed surprises. When astronomers first looked beyond the Milky Way, they discovered that our galaxy was not the universe. When they measured galaxy motion, they discovered expansion. When they measured that expansion carefully, they discovered acceleration. These discoveries were not predicted in detail beforehand. They emerged because we looked more closely than before. There is also a practical reason for building bigger and better instruments. Observations test theories. Cosmology relies on models that describe how matter, energy, space, and time interact. These models produce predictions. Those predictions must be checked against reality. When discrepancies appear, they signal either incomplete data or incomplete understanding. Without increasingly powerful telescopes, many questions would remain permanently speculative. We would be limited to extrapolation rather than evidence. Bigger eyes reduce the need to guess. Another motivation is less technical and more human. There is a quiet dissatisfaction in knowing that something exists beyond reach. When astronomers calculate that light from the first galaxy should be visible but cannot yet be detected, it creates a kind of tension, a gap between knowledge and ability. Building a new telescope becomes a way to close that gap. This pattern repeats across history. Radio telescopes opened an entirely new sky. X-ray observatories revealed violent processes invisible in optical light. Gamma-ray detectors exposed the most energetic events in the universe. Each time, astronomers discovered that what they could not previously see was not empty but busy. The universe does not become simpler the closer you look. It becomes more crowded. There is also a temporal aspect to this drive. Looking farther away means looking further back in time. Because light takes time to travel, distance becomes a record. The most distant objects are not just far, they are ancient. Observing them allows astronomers to reconstruct cosmic history directly rather than infer it. This is why early galaxies matter so much. They are not merely objects of curiosity, they are checkpoints. They reveal how quickly structure formed, how matter clumped, how stars ignited, and how chemistry evolved. If galaxies appear earlier or larger than expected, it suggests that the timeline we've drawn may need adjustment. James Webb's observations created precisely this kind of checkpoint tension. By seeing galaxies that appear surprisingly mature at early times, it challenges assumptions about the pace of cosmic evolution. And because these observations rely on infrared sensitivity that no previous telescope possessed, they could not have been made earlier. This highlights another reason we keep building bigger eyes. Each generation of instruments is shaped by the unanswered questions left behind by the previous one. Hubble revealed the early universe but hinted at deeper layers beyond its reach. Webb was designed specifically to explore those layers, and it will not be the last. Already, astronomers are discussing future observatories that could dwarf Webb in size or surpass it in precision. Concepts include massive space telescopes assembled in orbit, interferometers spanning thousands of kilometers, and detectors sensitive to gravitational waves rather than light. Each represents a different way of seeing, driven by the same underlying impulse. There is also a philosophical dimension to this effort. Seeing farther alters perspective. When the observable universe expands, even conceptually, it forces reconsideration of what feels central or significant. Earth moves further from the centre of attention, but the act of observation itself becomes more remarkable. We are not special because of where we are. We are notable because of what we attempt. The phrase "bigger eyes" can sound aggressive, as if we are trying to conquer the universe visually. In reality, it is more tentative. Each new instrument arrives with caution. Calibration takes years. Data is checked, rechecked, debated. Discoveries are announced carefully, often hedged with uncertainty. Science progresses slowly not because it lacks ambition, but because it respects the scale of what it studies. James Webb's design embodies this respect. Its deployment took weeks. Its calibration took months. Its observations are interpreted through layers of modelling and verification. The telescope itself does not proclaim conclusions. It delivers data. Humans argue gently over what that data means. And sometimes, the data suggests that the universe is larger, older, or stranger than anticipated. That realization does not invalidate previous efforts. It builds on them. Bigger eyes do not erase earlier views. They refine them. They add depth. They reveal that what once looked like a boundary was simply a limitation of perspective. As you consider this progression, from naked eye to Galileo's telescope to Hubble and now Webb, there is a continuity that becomes clear. Each step is motivated by the same question, asked in different forms. What else is there? And how can we see it more clearly? The question never receives a final answer. Each improvement generates new uncertainty. Yet the uncertainty is not unsettling in the way ignorance is. It is structured, informative. It narrows possibilities even as it expands horizons. There is something steady about this process. It does not rush. It does not demand resolution. It accepts that understanding unfolds over generations. The people who designed Webb knew they would not answer every question. They knew they were building a bridge, not a destination. As the telescope continues its work, the data it gathers will feed into models that describe the universe's size, age, and structure. Some of those models will bend, others will hold, new ones will be proposed. All of it will depend on the ability to see faint light from far away. And that brings us back to the central idea. We keep building bigger eyes because the universe keeps revealing that it has more to show. Not loudly, not dramatically, but quietly, through subtle mismatches between expectation and observation. Those mismatches are invitations. It's enough to recognize that every time humanity extends its sight, it does so with patience, caution, and a willingness to be surprised. And the universe, it seems, is always ready to return the favour. At first glance, it's tempting to think of a telescope as a very powerful pair of eyes, something that simply makes distant objects look closer. That idea works well enough for small backyard telescopes and even for some early observatories. But when you move into the realm of instruments like the James Webb Space Telescope, That description stops being accurate. Webb does not just magnify, it translates. It converts forms of information that would otherwise pass through the universe unnoticed into something we can study, measure, and slowly try to understand. To appreciate how unusual Webb's way of seeing really is, it helps to step away from the idea of vision as humans experience it. Human eyes are limited to a very narrow band of light, a small slice of the electromagnetic spectrum. We evolved to see what was useful for survival on the surface of a planet orbiting a star like the Sun. That range happens to be what we call visible light. It's comfortable, familiar, and deeply misleading when it comes to the universe at large. Most of what happens in the universe does not announce itself in visible light. Stars being born are often hidden behind thick clouds of gas and dust that block optical wavelengths. The earliest galaxies emit light that has been stretched far beyond what our eyes can detect. Even relatively nearby objects can appear dark or unremarkable in visible light while blazing with activity at other wavelengths. James Webb was built specifically to step outside the limits of human vision. Its primary sensitivity is in the infrared, a region of the spectrum just beyond red light. Infrared radiation is associated with heat, but in astronomy it's also closely tied to age and distance. The farther light travels through expanding space, the more its wavelength stretches. This process, known as redshift, moves light from higher energy wavelengths into lower energy ones. For the oldest and most distant objects, visible light becomes infrared by the time it reaches us. Earlier telescopes could detect some infrared, but not with the sensitivity Webb provides. Detecting faint infrared signals requires extreme care. Infrared radiation is everywhere. Warm objects emit it constantly. A telescope that is even slightly warm glows in infrared, drowning out the very signals it's trying to observe. This is why Webb looks the way it does. Instead of a solid tube like many telescopes, it carries a vast layered sun shield, roughly the size of a tennis court. This shield blocks sunlight, earthlight, and even moonlight, allowing the telescope's instruments to cool to extremely low temperatures. Some components operate just a few degrees above absolute zero. At those temperatures, their own infrared emission becomes minimal. This cooling is not a convenience. It is fundamental to Webb's vision. The mirror itself is another departure from tradition. Rather than a single piece of glass, Webb's primary mirror is made of 18 hexagonal segments, carefully aligned to act as one continuous surface. When fully deployed, it spans over 6 meters in diameter. This large collecting area allows Webb to gather more light from faint sources, increasing both sensitivity and resolution. The segmented design was not an aesthetic choice. A mirror that large could not fit inside any available rocket as a single piece. It had to fold, survive launch, and then unfold in space with astonishing precision. Each segment can be adjusted individually, allowing the mirror to be fine-tuned even after deployment. This ability to correct and refine is part of Webb's unusual way of seeing. Its vision is not static, it is actively maintained. Beyond the mirror, Webb's instruments are designed to do more than take pictures. They analyze light in detail. Spectroscopy, the process of breaking light into its component wavelengths, is one of Webb's most powerful tools. By studying these spectra, astronomers can determine the chemical composition of distant objects, their temperatures, their motions, and even the presence of molecules like water or carbon dioxide. This means Webb doesn't just show us where something is, it tells us what it's made of and how it's changing. Consider a distant galaxy detected by Webb. In visible light, it might appear as a faint smudge or not at all. In infrared, Webb can detect its glow, measure how much its light has been redshifted, and estimate its distance and age. By analysing spectral lines, astronomers can infer how rapidly stars are forming inside it, how massive it is, and how evolved its structure appears. This is where Webb's observations began to challenge expectations. Galaxies that appeared early in cosmic history, based on their redshift, were expected to be small, chaotic, and relatively dim. Instead, Webb found some that seemed surprisingly organised and bright. These observations did not rely on visual impressions alone. They were supported by spectral data that suggested significant stellar mass. Such findings depend critically on Webb's infrared sensitivity. Without it, these galaxies would blend into background noise or remain invisible altogether. Another aspect of Webb's vision is its location. Unlike Hubble, which orbits Earth, Webb operates near a point called the second Lagrange point, or L2. This is a region of space where the gravitational influences of Earth and the Sun balance in a way that allows a spacecraft to maintain a stable position relative to both. From this vantage point, Webb can keep its sunshield oriented consistently, with the Sun, Earth and Moon always on the same side. This stable thermal environment is essential for maintaining the low temperatures required for infrared observations. Operating at L2 also means Webb is far from Earth's heat and radiation, further reducing interference. This distance, however, comes with trade-offs. Webb cannot be serviced by astronauts. Once deployed, it must function largely on its own. Every component, from the mirror actuators to the instrument electronics, was designed with redundancy and longevity in mind. This self-reliance reinforces the sense that Webb is not merely an extension of earlier telescopes, it represents a different philosophy. Instead of building something that can be repaired easily, engineers built something that could avoid needing repair at all, while performing tasks no previous telescope could manage. The data Webb collects is also different in character. Infrared images often look unfamiliar. Structures that are dark in visible light may glow brightly. Dust clouds that obscure stars become translucent. Temperature differences reveal patterns invisible at other wavelengths. This unfamiliarity can be disorienting at first. It requires astronomers to recalibrate intuition. A bright infrared source is not necessarily visually bright. A dark region may not be empty. Webb's images must be interpreted carefully, with an understanding of what infrared light represents physically. This interpretive layer is part of what makes Webb's way of seeing unusual. It doesn't cater to human expectations. It reveals processes rather than appearances. When Webb observes a star-forming region, it can see through the dust that hides young stars from optical telescopes. This allows astronomers to study the earlier stages of stellar development. Similarly, Webb can detect heat signatures from planets orbiting other stars, providing clues about their atmospheres and potential habitability. But perhaps its most profound contribution lies in its ability to peer into the deep past. By detecting light emitted by some of the first galaxies, Webb acts as a time machine of sorts. Not in the sense of altering time, but in the sense of revealing snapshots of the universe at different stages of its evolution. Each observation adds a frame to a long, incomplete film. The unusual part is not just that Webb can see this far back, it's that it can see detail there. Structure, chemistry, motion. This level of detail was not anticipated fully. Models of early galaxy formation assumed gradual build-up. Webb's observations suggest that under certain conditions, structure may have emerged faster or more efficiently. Whether this means revising timelines, rethinking assumptions about dark matter, or refining models of star formation remains an open question. What matters is that Webb's way of seeing provides evidence that cannot be ignored. There is a temptation to anthropomorphize the telescope, to say that it looked too far or saw something it wasn't supposed to. In reality, Webb did exactly what it was designed to do. It gathered faint infrared light with unprecedented clarity. The surprise lies not in the instrument, but in the universe. This distinction is important. Webb does not impose interpretations, it delivers measurements. The unusual nature of its vision is not subjective, it is rooted in physics. Infrared light carries information about temperature, motion, and distance, in ways visible light cannot. As a result, Webb expands not only what we see, but how we think about seeing itself. Astronomy often advances by challenging the reliability of intuition. What looks empty may be full. What looks distant may be closer in cosmic terms. What looks simple may be layered with complexity. Webb amplifies this effect. Its observations force astronomers to rely more heavily on data analysis, and less on visual familiarity. The universe becomes less like a picture and more like a data set, rich with signals that require careful interpretation. This shift has consequences for how the size of the universe is discussed. Distance estimates rely on redshift measurements, which Webb excels at. Mass estimates rely on light output and spectra, which Webb provides in detail. If those measurements differ systematically from previous expectations, then conclusions about scale must adapt. This does not mean that earlier telescopes were wrong. They were limited by the technology available at the time. Webb's unusual way of seeing simply extends the range of inquiry. As observations accumulate, patterns will emerge. Some early surprises may resolve into consistency. Others may persist, pointing toward gaps in current models. Either way, Webb's role is to supply evidence, not closure. The universe is not obligated to align with our expectations, and Webb's design acknowledges that implicitly. By removing constraints imposed by atmosphere, temperature, and wavelength sensitivity, it opens a window that had never existed before. Looking through that window requires patience. The data must be processed, calibrated, and debated. Early interpretations may change. That is part of the process. What remains constant is the shift in perspective. Webb does not show us the universe as we see it. It shows us the universe as it emits and transforms light across vast stretches of space and time. There is a subtle misunderstanding that often follows astronomy around, especially when telescopes like James Webb are involved. People will sometimes say that astronomers are deliberately trying to look into the past, as if time itself were the main target. In reality, no one sets out to chase history directly. What astronomers pursue is light. Time simply comes along for the ride. The reason this happens is woven into how the universe works at a very basic level. Light does not arrive instantly. It travels at a finite speed, fast enough to feel immediate in everyday life, but slow enough to matter enormously across cosmic distances. When you look at the moon, you are seeing it as it was a little over a second ago. When you look at the sun, you're seeing it as it was about 8 minutes ago. These delays are so small, they rarely register as meaningful. But as distance increases, the delay grows, and eventually it becomes impossible to ignore. This is where astronomy quietly turns into archaeology. When James Webb observes a galaxy billions of light years away, it is not showing that galaxy as it exists now. It is showing how it looked when the light left it, long before Earth existed, long before the Sun formed, long before the Milky Way had its current shape. Webb is not choosing to look back in time. It cannot avoid doing so. What makes this particularly striking is that there is no clear boundary where looking far turns into looking back. There is no signpost that says, "Past begins here." The transition is gradual, seamless, and unavoidable. Every additional unit of distance adds another slice of history. For nearby stars, the past is shallow. For distant galaxies, it is deep. For the most distant objects Webb can detect, the past approaches the universe's earliest chapters. This has always been true of astronomy, but Webb amplifies it dramatically. Its sensitivity allows it to detect light that has travelled for over 13 billion years. That means it is observing the universe not long after the first stars ignited. At that point, the cosmos was a very different place. It was smaller, hotter, denser, and far less structured. The strange thing is that when astronomers designed Webb, they did not fully know what those early scenes would look like. Models suggested faint, primitive objects, irregular shapes, small clumps of stars just beginning to form. Webb's job was to test those expectations, not confirm them by assumption. What it found instead raised questions. Some of the galaxies Webb observed at extreme distances appear surprisingly developed. They show signs of structure and mass that imply significant star formation had already taken place. This suggests that cosmic evolution may have progressed faster than previously thought, or that the conditions in the early universe were more efficient at building structure. To understand why this matters, it helps to think about how cosmic time is reconstructed. Astronomers do not have a single clock they can point at the universe. Instead, they piece together timelines using observations at different distances. Nearby objects show the present or recent past. Farther objects show earlier stages. By assembling these observations, they attempt to reconstruct a continuous narrative. This narrative depends on assumptions. It assumes that physical laws behave consistently over time. It assumes that certain relationships between brightness, mass, and distance hold true. It assumes that redshift accurately reflects expansion. When Webb's observations don't fit neatly into this narrative, it doesn't mean time has behaved strangely. It means our reconstruction may be incomplete. One of the most important concepts here is cosmic look-back time. This refers to how far into the past we're seeing when we observe a distant object. Look-back time is not the same as distance in space, although the two are related. Because the universe has expanded while the light was travelling, the distance to an object now is greater than the distance it was when the light was emitted. This leads to a layered understanding of space. There is the distance light has travelled, there is the current distance between objects, and there is the age of the universe at the moment the light was emitted. Webb's observations operate within this layered framework. When Webb detects a galaxy with a high redshift, it indicates that the light has been stretched significantly by cosmic expansion. That stretching suggests the light has travelled for a very long time. From this, astronomers estimate how long ago the light was emitted and thus how old the universe was at that time. This is where the phrase, looking back in time, becomes unavoidable. But it's important to remember that nothing is being rewound. No signal is being retrieved from the past deliberately. The light has been travelling continuously since it was emitted. It is only now reaching Webb's detectors. In a sense, the universe is constantly delivering its own history to us, one photon at a time. James Webb's unusual ability lies in catching photons that were previously too faint or too stretched to detect. Earlier telescopes could only reach so far before the signal disappeared into noise. Webb pushes that boundary outward, which also pushes the look-back time deeper. This extension has consequences. The farther back we look, the less settled the universe appears. Structures are forming, matter is clumping, energy is redistributing. The familiar order we see nearby has not yet fully emerged, and yet Webb's observations suggest that some order emerged earlier than expected. This creates a subtle tension. If galaxies were forming and growing rapidly early on, then the timeline of cosmic history may need adjustment. Alternatively, if the galaxies appear older or larger due to misinterpretation of data, then measurement techniques must be refined. Either way, the act of looking back exposes uncertainties that were less visible before. There is also an emotional component to this, even if it is rarely acknowledged. Seeing the universe as it was billions of years ago invites reflection, not in a poetic or abstract sense, but in a practical one. It reminds us that what we call now is a local experience. Across the universe, different regions are effectively living in different observed times, depending on where the observer is. From Webb's perspective, every direction is a window into a different era. This challenges the intuition that time is uniform and shared. On Earth, time feels synchronized. Clocks tick together. Days pass collectively. In the universe at large, simultaneity breaks down. Two galaxies separated by vast distances cannot meaningfully agree on what now means, even in principle. Relativity formalized this idea long ago, but Webb's observations make it tangible. When we look at a distant galaxy, we're not seeing a simultaneous counterpart to our present. We are seeing a preserved moment. This preserved moment is not static. The galaxy has continued evolving since the light left it. Stars have aged. Supernovae have occurred. Structures have changed. Webb cannot access that updated state yet, and may never be able to if expansion continues to accelerate. So the image we receive is both real and incomplete. This incompleteness is not a flaw, it is a feature of cosmic observation. Astronomy deals not with instantaneous states, but with histories in transit. The deeper Webb looks, the more pronounced this becomes. At extreme look-back times, we approach the era when the first stars formed. Before that, there was a period known as the Cosmic Dark Ages, when the universe had cooled enough for atoms to form, but not yet enough for stars to ignite. During that time, there were no luminous objects to observe. Webb's sensitivity edges close to this boundary. It does not see darkness itself, but it sees the earliest light emerging from it. This proximity to the beginning amplifies every discrepancy. Small differences in observation correspond to large differences in interpretation. A galaxy appearing a few 100 million years earlier than expected can challenge entire models of structure formation. It is here that the phrase "without meaning to" becomes important. Astronomers did not set out to disrupt timelines. They set out to observe faint infrared light. The disruption arises because the universe, when viewed at these depths, does not always behave as anticipated. The telescope does not choose which era to reveal. It simply receives what arrives. Another subtlety is that looking back in time is not uniform across wavelengths. Different types of light reveal different aspects of the past. Infrared light traces stars and dust. Radio waves trace neutral hydrogen. X-rays trace energetic events. Webb's focus on infrared emphasizes certain processes over others. This selective emphasis shapes interpretation. Early galaxies may appear more massive in infrared because that light traces older, cooler stars. Without complementary data from other wavelengths, conclusions must be drawn carefully. Astronomers are aware of this. Webb's data is often combined with observations from other telescopes to build a more complete picture. Even so, the infrared view remains uniquely powerful for early cosmic history. There is also the matter of cosmic expansion itself. As Webb looks farther back, it looks into a universe that was expanding at different rates. The expansion history affects how light travels and stretches. This means that translating redshift into time requires assumptions about the universe's expansion rate and its contents, including dark energy and dark matter. If those assumptions are slightly off, time estimates shift. This is one reason why Webb's observations are connected to questions about the size of the universe. Time, distance, and expansion are intertwined. Looking back farther than expected forces re-evaluation of how big the observable universe is and how its growth has unfolded. Again, this is not because Webb intended to challenge these ideas. It is because improved observation reveals where models are stretched thin. There is a quiet humility in this process. Scientists do not treat Webb's images as final answers. They treat them as evidence that must be integrated carefully. Papers are written, debated, revised. Some early claims are softened, others persist. What remains constant is the fact that looking deeper necessarily means looking earlier. For someone listening quietly, perhaps late at night, this idea does not need to feel overwhelming. It can be taken at face value. The universe sends out light continuously. That light carries information about when and where it was emitted. Webb catches some of the oldest light we can detect. In doing so, it reveals earlier versions of reality. This does not mean the past is fixed in interpretation. Our understanding of it evolves as new data arrives. The past we reconstruct today is not the same as the past reconstructed 50 years ago. It is more detailed, more nuanced, and sometimes more confusing. That confusion is productive. For a long time, astronomers were comfortable with the idea that the early universe was messy and slow to organise. Not chaotic in the sense of randomness, but tentative. Matter had only recently begun to clump together. Gravity was working, but it hadn't had much time to do its job. The first stars were expected to be small, short-lived and scattered. The first galaxies, by extension, were assumed to be modest collections of those stars, irregular in shape and limited in mass. That expectation wasn't based on guesswork. It came from decades of theoretical work, computer simulations, and observations made with earlier telescopes. Models of cosmic evolution suggested a gradual build-up. Tiny fluctuations in the density of matter shortly after the Big Bang would slowly grow under gravity. Dark matter would form invisible scaffolding. Gas would fall into those structures. Stars would ignite. Over hundreds of millions of years, small systems would merge into larger ones. In this picture, size came late. So when James Webb began returning images and data that hinted at surprisingly large and well-developed galaxies very early in cosmic history, the reaction was not excitement first. It was hesitation. Because these galaxies appeared where they shouldn't be, not spatially, but temporally. To understand why that matters, it helps to be clear about what early means in this context. When astronomers talk about the first galaxies, they're referring to objects observed at extremely high redshifts. These redshifts correspond to times when the universe was only a few 100 million years old. In human terms, that is unimaginably ancient. In cosmic terms, it is infancy. At that stage, there simply hadn't been much time for stars to form, live, and die. Heavy elements were scarce. Structures were expected to be fragile and incomplete. Yet Webb detected galaxies at these redshifts that seemed bright, massive and structured. Brightness alone is not enough to cause concern. A small galaxy with a burst of star formation can shine intensely for a brief period. But Webb's observations went beyond brightness. Spectral analysis suggested significant stellar mass. Not just a handful of stars, but large populations. Enough to imply sustained star formation over time. That implication immediately raised a question. Where did all that mass come from so quickly? In standard cosmological models, the pace of early star formation is constrained by several factors. Gas must cool before it can collapse into stars. Cooling depends on the presence of certain elements. Those elements are produced by earlier generations of stars. It's a feedback loop that takes time to ramp up. Seeing mature galaxies so early suggests either that this process was far more efficient than expected, or that some assumptions about early conditions are incomplete. Astronomers are cautious by nature, especially when observations challenge well-established frameworks. The first step was not to rewrite textbooks, but to interrogate the data. Were the redshifts accurate? Were the mass estimates reliable? Could dust be affecting the measurements? Could these objects be something else entirely? James Webb's instruments are precise, but interpretation is never straightforward. Estimating the mass of a distant galaxy involves modelling its light. Different stellar populations produce different spectral signatures. Dust can obscure or redden light. Active galactic nuclei can add extra brightness. Each of these factors had to be considered carefully. Even after accounting for uncertainties, some of the galaxies remained difficult to reconcile with expectations. They were not isolated anomalies. They appeared in multiple fields of observation. Different research teams reported similar findings independently. This pattern made it harder to dismiss the results as statistical flukes. What made the situation more intriguing was not just the existence of these early galaxies, but their apparent diversity. Some appeared compact and dense, others more extended. Some showed signs of rapid star formation, others seemed calmer. This variety suggested that galaxy formation was not a single, uniform process even at very early times. That too was unexpected. The prevailing view had been that early galaxies would look broadly similar, shaped primarily by the same simple physical processes. Webb's observations hinted a richer landscape, even near the beginning. This does not necessarily mean the models are wrong. It may mean they are incomplete. One possibility is that dark matter behaved differently in the early universe than models assume. Dark matter is thought to dominate the mass budget of galaxies and to play a crucial role in structure formation. If its properties or interactions allowed matter to clump more efficiently early on, galaxies could grow faster. Another possibility involves the nature of the first stars. The earliest stars, often referred to as population 3 stars, are thought to have been massive and short-lived. If they formed in large numbers and enriched their surroundings quickly, they could have accelerated subsequent star formation. There is also the role of mergers. Small galaxies merging into larger ones is a key mechanism in cosmic evolution. If mergers were more frequent or more efficient early on, mass could accumulate rapidly. Webb's resolution allows astronomers to see structures that may indicate early merging activity. Each of these explanations has implications beyond galaxy formation. They affect our understanding of reionization, the process by which the universe transitioned from opaque to transparent. They influence estimates of how quickly heavy elements spread. They shape predictions about the number and distribution of galaxies at different times. This is why the placement of these galaxies matters so much. They don't just appear early, they appear early enough to strain multiple interconnected ideas. It's worth emphasizing that appearing where they shouldn't be does not mean they violate physical laws. It means they don't align neatly with expectations derived from those laws as currently understood. Science advances precisely through this kind of misalignment. There is also a subtle observational bias at play. Webb is extraordinarily good at detecting bright objects. If early galaxies underwent brief periods of intense star formation, Webb might preferentially detect those, while missing fainter, quieter systems. This could skew the apparent population. Astronomers are actively investigating this possibility. Deeper surveys over wider areas will help determine whether the observed galaxies are representative or exceptional. Even so, the fact remains that Webb has extended our observational reach into a regime that was previously inaccessible. In doing so, it has revealed objects that force reconsideration of timelines. Timelines in cosmology are delicate things. They are built from overlapping evidence, not direct measurement. When new evidence shifts one part of the timeline, other parts must adjust. This is where discussions about the size of the universe quietly re-enter the picture. If galaxies formed earlier and grew faster, then the observable universe may contain more structure at greater distances than anticipated. That does not necessarily mean the universe is physically larger, but it does affect how much of it is observable and how densely populated that observable region is. Density matters. A universe that forms structure quickly looks different from one that takes its time. It influences how light travels, how ionization unfolds, and how expansion interacts with matter. James Webb's early galaxy observations suggest a universe that may have been more efficient at building complexity than previously thought. This efficiency has consequences for how we interpret redshift itself. Redshift tells us how much the universe has expanded since the light was emitted, but translating that expansion into age assumes a particular expansion history. If early structure formation influences that history in subtle ways, age estimates could shift. Again, this does not imply a dramatic revision overnight. It implies refinement. Astronomers are now working to understand whether these early galaxies represent the upper end of a distribution, or whether the distribution itself needs adjustment. Are these galaxies rare outliers, or common residents of the early universe? Answering that requires time, patience, and more data. Webb will continue observing. Other telescopes will complement its findings. Simulations will be updated. Assumptions will be tested. Some early interpretations will change, others will strengthen. This process is slow by design. The important takeaway is not that the universe is broken or that science is failing. It is that our picture of the early universe is becoming more detailed, and detail often complicates simple stories. The first galaxies are not politely waiting their turn according to our expectations. They are revealing themselves according to their own history. That history may include faster cooling, more efficient star formation, or interactions we do not yet fully understand. It may involve physics that operates subtly differently under early conditions. Or it may simply reflect that the universe has always been better at building structure than we gave it credit for. What is clear is that these galaxies, by appearing where they shouldn't in time, are inviting a closer look at the assumptions underlying cosmic evolution. They are not anomalies to be dismissed. They are data points to be integrated. Distance feels like one of the most reliable ideas we have. In everyday life, it behaves politely. A room has a size you can walk across. A road has a length you can drive. A journey takes longer if it covers more ground. These expectations are so deeply ingrained that it's easy to assume distance always works this way, no matter the scale. For a long time, astronomy relied on that same intuition, just stretched outward. Stars were farther than planets. Galaxies were farther than stars. The universe was big, but distance still felt like distance. The problem is that this intuition begins to fail quietly, not all at once, but gradually, as observations push farther out. James Webb did not break the concept of distance. It revealed how conditional it has always been. In cosmology, distance is not a single thing. It is a collection of definitions that depend on context, assumptions, and what exactly you're trying to measure. This is manageable when objects are relatively nearby. It becomes complicated when the universe itself is changing while light is travelling through it. To see why this matters, consider something simple. If you shine a flashlight across a dark field, the light travels through static space. The distance between you and the far end of the field does not change while the light moves. The time it takes for the light to arrive is directly related to how far away the target is. This relationship feels obvious. Now replace the field with the universe. Space is not static. It expands. And it has been expanding for the entire time that light from distant galaxies has been travelling toward us. That means the distance between the source and the observer is not fixed. It changes continuously during the journey. This single fact undermines almost every intuitive notion of distance. When astronomers say that a galaxy is, for example, 10 billion light-years away, that statement hides layers of interpretation. Is that the distance light has travelled? Is it the distance to the galaxy now? Is it the distance at the time the light was emitted? Each of these answers is different, and all of them can be correct depending on the definition being used. James Webb operates at distances where these distinctions stop being academic and start being essential. One of the most commonly used distance measures in cosmology is look-back distance, which corresponds to look-back time. This is the distance light has effectively travelled over time. If light has been travelling for 10 billion years, then the look-back distance is 10 billion light-years. This feels straightforward, and it aligns nicely with the idea of looking back in time. But the universe did not remain the same size during those 10 billion years. It expanded significantly. As a result, the galaxy that emitted the light is now much farther away than 10 billion light-years. This leads to another measure called comoving distance. Comoving distance accounts for expansion and describes how far away objects are in a coordinate system that expands with the universe. In comoving terms, the most distant galaxies we can observe are roughly 46 billion light-years away, even though the universe is only about 13.8 billion years old. Already, distance has stopped behaving the way everyday experience would suggest. James Webb's observations push deep into this regime. The galaxies it detects at high redshift are not just far. They are far in a way that depends on how you define far. When astronomers plot these galaxies on cosmic maps, their placement shifts depending on which distance measure is used. This has practical consequences. Galaxy brightness depends on distance. Size estimates depend on distance. Mass estimates depend on distance. If distance itself is a moving target, then all derived properties inherit that uncertainty. Before Webb, many of these issues were present but manageable. Observations did not reach far enough for the ambiguities to dominate. Webb's sensitivity changes that balance. It brings into focus objects for which small changes in distance assumptions lead to large changes in interpretation. This is especially true when it comes to early galaxies. As discussed earlier, Webb has detected galaxies that appear unexpectedly large and massive at early times. Part of this impression depends on how far away they are assumed to be. If a galaxy is farther than initially estimated, its intrinsic brightness must be higher to appear as bright as it does. That implies more stars, more mass, and more rapid formation. If the distance estimate shifts even slightly, the inferred properties can change dramatically. Redshift plays a central role here. Redshift is often treated as a proxy for distance, but strictly speaking, it measures how much the universe has expanded since the light was emitted. Translating redshift into distance requires a cosmological model. That model includes assumptions about the expansion rate of the universe over time, the density of matter, and the influence of dark energy. Those assumptions are based on the best available data, but they are not immune to revision. James Webb's observations intersect with this model in a subtle way. By detecting galaxies at high redshift with unexpected properties, Webb indirectly tests whether the model's assumptions hold under early conditions. If they do not, then the mapping between redshift and distance may need refinement. This does not mean redshift is wrong. It means its interpretation is conditional. Another layer of complexity arises from the fact that distance is not observed directly. Astronomers infer it using standard candles, standard rulers, and statistical relationships. Each method carries uncertainties. Webb does not eliminate those uncertainties. It exposes where they matter most. For nearby galaxies, distance uncertainties might be a few percent. For the most distant galaxies, those uncertainties can be much larger, especially when combined with assumptions about early star populations and dust content. When distance stops behaving intuitively, astronomers are forced to confront how much of their understanding relies on extrapolation. There is also the issue of cosmic horizons. The observable universe has a limit not because there is an edge, but because light has only had so much time to reach us. Beyond that horizon, regions of the universe exist that are causally disconnected from us. We cannot see them, and they cannot see us, at least not yet. James Webb does not cross this horizon, but it approaches it closely enough to make its implications concrete. Objects near the horizon are observed as they were very early on, and their current distance is vastly greater than their look-back distance. This disconnect between what we see and where things are now makes the concept of where feel less solid. When astronomers say that Webb found galaxies at certain distances, they are condensing a complicated set of relationships into a manageable phrase. The underlying reality is more fluid. Distance at these scales is not a single number. It is a function of time, expansion, and perspective. This realization feeds directly into discussions about the size of the universe. If distance depends on how expansion is modelled, then the size of the observable universe depends on those same assumptions. Webb's data does not necessarily imply a larger universe, but it does tighten constraints on how large it could be. More importantly, it reveals that the observable universe is richly populated all the way out to its limits. The density of structure challenges earlier expectations that the farthest reaches would be sparse and simple. Another reason distance becomes slippery is gravitational lensing. Massive objects bend space, causing light from background galaxies to follow curved paths. This can magnify and distort distant objects, making them appear brighter or larger than they otherwise would. Webb's resolution allows astronomers to detect subtle lensing effects. In some cases, early galaxies may appear unusually prominent because their light has been magnified by intervening mass. Correcting for this requires careful modelling of the foreground structures. Again, distance estimation becomes intertwined with interpretation. None of this suggests confusion or failure. It suggests that distance, at cosmic scales, is a derived quantity, not a primitive one. It is calculated, not measured with a ruler. James Webb's role in this process is not to simplify distance, but to force clarity about how it is defined and used. As observations accumulate, astronomers refine distance ladders, adjust models, and improve consistency across methods. Webb provides anchor points at extreme distances that were previously inaccessible. These anchor points help test whether different distance measures agree where they overlap. Sometimes they do, sometimes they don't. When they don't, it signals an opportunity to learn something new about cosmic expansion, dark energy, or early structure formation. There is also a psychological aspect to this shift. Distance feels like a grounding concept. Losing its simplicity can feel destabilizing. But in science, losing simplicity often means gaining accuracy. The universe does not owe us intuitive behavior. As distance stops meaning what we thought it did, astronomers adapt by being explicit. Papers specify which distance measure is being used. Figures include multiple axes. Discussions acknowledge uncertainty. This precision replaces intuition. The farther Webb looks, the less distance behaves like a straight line between 2 points. Instead, it behaves like a record of expansion, layered with time and shaped by gravity. What matters is not memorizing the different definitions, but understanding why they exist. They exist because space itself changes. James Webb did not create this complexity. It revealed it more clearly than before. Trying to measure the size of the universe sounds at first like a contradiction. Size implies boundaries. It suggests edges, limits, something you can place a ruler against. The universe offers none of those comforts. There is no outer wall to lean on, no corner to mark, no place where space politely stops and says, "This is as far as it goes." And yet astronomers talk about the size of the universe with confidence, numbers, diagrams, and carefully chosen definitions. They do this not because the universe is finite in an everyday sense, but because measurement in science is often about framing questions precisely enough that answers become possible. The key to understanding how astronomers measure something endless is realizing that they are not measuring the whole thing. They are measuring what can be accessed, inferred, or constrained. The universe may be infinite, it may be finite but unbounded, it may have a shape that defies simple intuition. None of that prevents measurement, it just changes what measurement means. The most common phrase you will hear is the observable universe. This is not a poetic term, it is a technical one. The observable universe refers to the region of space from which light has had time to reach us since the beginning of cosmic expansion. Because the universe has a finite age and light travels at a finite speed, there is a limit to how far we can see. That limit defines a sphere centered on the observer, not because the universe is centered on us, but because observation always has a point of reference. From Earth, the observable universe extends in all directions. Its radius is not the age of the universe in light years, as intuition might suggest, but much larger. Due to the expansion of space, light that took about 13.8 billion years to reach us originated from regions that are now far farther away. When expansion is accounted for, the radius of the observable universe comes out to roughly 46 billion light-years. That number is already strange. It tells us that the observable universe is more than 3 times larger in radius than the age of the universe might naively imply. But even this is only the size of what we can see, not the size of what exists. Astronomers are careful to make this distinction. When they speak about measuring the size of the universe, they are often referring to the size of the observable universe, or to constraints on the geometry of the universe as a whole. These are different questions, approached in different ways. One way to probe the universe's size is through geometry. Geometry in this context does not mean measuring angles in triangles drawn on paper. It means determining whether space itself is flat, positively curved, or negatively curved. These terms have precise meanings. A flat universe follows the rules of Euclidean geometry. Parallel lines stay parallel. The angles of a triangle add up to 180 degrees. A positively curved universe is more like the surface of a sphere. Parallel lines eventually meet. Triangle angles add up to more than 180 degrees. A negatively curved universe resembles a saddle. Parallel lines diverge. Triangle angles add up to less than 180 degrees. The geometry of the universe is closely tied to its size. A positively curved universe is finite. It has a total volume, even though it has no edges. A flat or negatively curved universe can be infinite. To measure this geometry, astronomers look for large-scale patterns. One of the most important tools is the cosmic microwave background, the faint radiation left over from the early universe. This radiation fills all of space and carries subtle variations in temperature. Those variations reflect sound waves that rippled through the hot plasma of the early universe. By measuring the apparent size of these fluctuations on the sky, astronomers can infer the geometry of space. If the universe is curved, those patterns appear larger or smaller than they would in a flat universe. Measurements from satellites like WMAP and Planck have shown that the universe is very close to flat, within small margins of error. This suggests that if the universe is finite, it is extremely large, possibly much larger than the observable universe, possibly infinite. James Webb does not measure the cosmic microwave background directly, but its observations connect to this picture by mapping the distribution of galaxies at great distances. Large-scale structure offers another way to test geometry and size. If the universe was small enough that light could wrap around it, we might see repeating patterns, the same galaxy appearing in different directions. So far, no such repetitions have been found. This absence does not prove infinity. It sets a lower bound on size. The universe must be at least larger than the observable region we can survey. This idea of setting bounds rather than finding exact values is central. Astronomers often cannot say how big the universe is. They can say how small it is not. Another approach involves measuring expansion itself. The expansion rate of the universe, described by the Hubble parameter, changes over time. By studying how galaxies move away from each other at different distances, astronomers can reconstruct the expansion history. This history depends on the contents of the universe, including matter, radiation, and dark energy. The expansion history influences the relationship between redshift and distance. James Webb contributes here by extending reliable redshift measurements deeper into the past. The farther back we can measure expansion accurately, the better we can constrain models of the universe's growth. Those models, in turn, affect estimates of size. A universe that expanded rapidly early on will have a different observable radius than one that expanded more slowly. Webb's observations help refine these timelines. Another method involves standard candles, objects of known intrinsic brightness. Type Ia supernovae are a classic example. By comparing how bright they appear to how bright they should be, astronomers estimate distances. Webb's infrared sensitivity allows it to observe supernovae at greater distances and with less interference from dust. This improves distance estimates at high redshift. Distance ladders are built by combining multiple methods. Parallax measures nearby stars. Cepheid variables extend reach further. Supernovae reach farther still. Each rung overlaps with the next, providing calibration. Webb strengthens some of these rungs, particularly at the high redshift end. But even with precise distance measurements, size remains elusive because the universe does not present itself all at once. It reveals itself through light that arrives over time. Measuring size becomes an exercise in interpreting arrival times, wavelengths, and distributions. There is also the distinction between physical size and coordinate size. In an expanding universe, coordinates can be chosen in different ways. Comoving coordinates expand with the universe, keeping galaxies at fixed positions in the grid. Proper distances change as space expands. Both descriptions are valid. They describe different aspects of reality. When astronomers say the observable universe has a radius of 46 billion light-years, they are referring to comoving distance. This describes how far away those regions are now, not how far the light travelled. Without careful language, these distinctions can blur. James Webb's role in all this is not to provide a single definitive measurement of cosmic size. It is to populate the far reaches of the observable universe with data. Galaxies, clusters, star formation rates, chemical abundances. Each data point constrains models, each constraint narrows the range of possible sizes. An endless universe does not mean unmeasurable, it means measurable in pieces. There is also a philosophical shift required here. Measuring the universe is not like measuring a room. It is more like inferring the size of a forest by studying the trees you can see and understanding how forests grow. You never see the whole thing. You see patterns, densities, edges of visibility. The fact that the universe may be infinite does not paralyze science. It motivates it. Infinity becomes a context rather than an obstacle. James Webb complicates this picture by revealing that the farthest regions we can observe are more structured than expected. This affects how astronomers think about homogeneity. The universe is assumed to be homogeneous and isotropic on large scales. That means it looks roughly the same everywhere when averaged over large enough volumes. Webb's observations test this assumption by pushing those volumes farther out. If early structure is denser or more varied than expected, it could hint at subtle deviations from homogeneity. That would have implications for size estimates and cosmological models. So far, the evidence still supports large-scale uniformity, but the margins are being explored more thoroughly than before. Another subtle point is that measuring size also involves deciding what question you're asking. Are you asking how far light can travel? How much volume is observable? Whether space wraps around? Whether the universe has a finite total volume? These are related but distinct questions. Astronomers use different tools for each. James Webb primarily informs questions about observability and structure. It tells us how populated the observable universe is at its edges. It tells us how early complexity arose. It does not directly tell us whether the universe is infinite, but it helps rule out certain possibilities. For example, a very small finite universe would likely show repeating patterns or correlations at large scales. The absence of these patterns suggests a minimum size. Webb extends the scale at which this absence is confirmed. There is also the question of whether the observable universe is representative of the whole. Cosmology assumes it is. This assumption is called the cosmological principle. It states that the universe is statistically similar everywhere on large scales. If this principle holds, then studying one region tells us about others. James Webb's observation tests this principle at early times. If early galaxies are similar across different regions, it supports the idea that the observable universe is a fair sample. So far, Webb's data suggests remarkable consistency. Differences exist, but not radical departures. This consistency supports the use of observable measurements to infer global properties. In this way, astronomers measure the size of something endless by combining observation, theory, and constraint. They accept that they cannot see everything. They focus on what can be seen and what must follow from it. This process is slow and iterative. Each new telescope refines bounds rather than closing cases. James Webb is no exception. As the picture becomes clearer, one thing stands out. The universe does not become simpler as we push toward its limits. It becomes more subtle. Measurement becomes an art of careful definition. The size of the universe is not a single number waiting to be discovered. It is a range shaped by what we can observe, how space behaves, and how light travels. James Webb did not find the edge of the universe. It helped clarify how far the edge of observation reaches and how rich that edge is. For most of human history, size felt like a fixed property. Mountains stayed where they were. Oceans did not quietly stretch wider overnight. A city might grow, but the land beneath it did not expand. Even when astronomy first began to deal with large scales, the universe itself was imagined as a stable container. Stars moved within it. Planets traced paths, but the stage stayed the same size. That assumption did not collapse all at once. It eroded slowly, and only because observations forced it to. The idea that the universe refuses to stay the same size is not intuitive, and it is still one of the hardest concepts to internalize, even for people who work with it every day. Expansion does not behave like an explosion. It does not have a center. It does not push galaxies through space the way debris flies outward from a blast. Instead, space itself changes. The distances between distant objects increase because the fabric connecting them stretches. This distinction matters because once space itself becomes dynamic, size stops being a static descriptor and turns into a process. The first hints of this came in the early 20th century, when astronomers began measuring the light from distant galaxies and noticing systematic shifts toward the red end of the spectrum. At first, these shifts were puzzling. Redshift could be caused by motion, like the Doppler effect, but the scale of the effect was unusual. Nearly every galaxy showed it, and the farther away a galaxy was, the stronger the shift appeared to be. Edwin Hubble and others eventually recognized the pattern. Galaxies were not simply moving randomly. On average, they were moving away from each other, and the farther apart they were, the faster that separation increased. This observation led to a conclusion that was unsettling at the time. The universe was expanding, not metaphorically, not in some abstract mathematical sense. Literally, space itself was getting larger. Once this idea was accepted, the concept of a fixed cosmic size became obsolete. If the universe is expanding now, then it must have been smaller in the past. And if expansion continues, it will be larger in the future. Size becomes a function of time. James Webb enters this story not as the discoverer of expansion, but as a witness to its long-term consequences. When Webb looks at distant galaxies, it is not just seeing them as they were long ago. It is seeing them embedded in a universe that was physically smaller. The distances between galaxies were shorter. The average density of matter was higher. Interactions were more frequent. This context is essential for interpreting what Webb observes. Consider the early galaxies that appeared unexpectedly large and developed. Part of what makes them surprising is that they formed in a universe that had not yet expanded very much. The volume available for matter was smaller, gas densities were higher, gravity had less distance to work with. In such conditions, structure formation could proceed differently. This does not automatically resolve the tension, it reframes it. Instead of asking how galaxies grew so large so early, astronomers ask how expansion rate, density and cooling interacted in those early epochs. Expansion rate matters because it sets the pace at which matter spreads out. A faster expanding universe makes it harder for gravity to pull matter together. A slower expanding universe allows clumping to proceed more easily. Current cosmological models describe an expansion history that changes over time. Early on, expansion slowed as matter dominated. Later, it began accelerating again due to dark energy. James Webb's observations probe the era before dark energy became dominant. During this period, the universe was slowing its expansion, allowing structures to grow more efficiently. The degree of that slowing affects how quickly galaxies can form. If Webb's data suggests that structure formed faster than expected, it could imply that expansion slowed more than models predict, or that matter behaved in ways not fully captured. This is where the phrase, refusing to stay the same size, takes on layered meaning. The universe does not just expand. The rate of expansion itself changes. Sometimes it decelerates. Sometimes it accelerates. The scale of everything is in motion, but not uniformly. Understanding this requires separating several related ideas that are often conflated. First, there is the expansion of space itself. This describes how distances between unbound objects increase over time. Second, there is the expansion rate, which tells us how quickly those distances increase at a given moment. Third, there is acceleration or deceleration, which describes how the expansion rate changes. James Webb's data feeds into all three. By measuring redshifts accurately and combining them with brightness and structure information, astronomers can infer how fast the universe was expanding when the light was emitted. Doing this for many objects at different epochs builds a timeline of expansion. Before Webb, much of this timeline relied on relatively sparse data at high redshift. Webb fills in gaps, especially in the era when the first galaxies formed. This matters because the size of the observable universe depends not just on how long the universe has existed, but on how expansion unfolded during that time. If expansion was slower early on than assumed, light from distant regions could travel farther before being carried away by expansion. That would increase the observable radius. If expansion was faster, the opposite would occur. Thus, measuring expansion history is inseparable from measuring size. Another layer of complexity comes from the fact that not everything expands equally. On small scales, gravity dominates. Galaxies do not expand internally, neither do solar systems or atoms. Expansion becomes significant only over vast distances where gravity is weak compared to the overall stretching of space. This selective expansion complicates intuition. The universe expands, but not like a balloon inflating uniformly at every scale. It expands between galaxies, not within them. James Webb observes objects that sit near the boundary between these regimes. Early galaxies were closer together, interactions were common, mergers occurred frequently. The distinction between bound and unbound structures was still forming. As the universe expanded, these structures became more isolated. Distances grew, interaction rates declined. This evolutionary process is visible indirectly through Webb's observations. The distribution and properties of galaxies change with redshift. Early universes look denser and more active. Later universes look more spread out and calmer. This changing appearance reflects the universe's refusal to stay the same size. There's also the role of dark energy, which adds a further twist. Dark energy appears to drive the accelerated expansion of the universe at late times. Its nature remains unknown, but its effect is measurable. As dark energy becomes dominant, expansion accelerates. Distant galaxies recede faster and faster. Eventually, regions of the universe become causally disconnected. Light emitted beyond a certain distance will never reach us. This creates an evolving, observable universe. The boundary of what can be seen is not fixed in time. It grows as light arrives, but it also changes character as expansion accelerates. James Webb observes a universe that has not yet entered its dark, energy-dominated future. But understanding its observations requires placing them within this broader expansion narrative. The refusal of the universe to stay the same size is not a problem to be solved. It is a property to be described. Historically, accepting this property required abandoning comfortable ideas. Static universes were simpler to imagine. An expanding universe introduced questions about beginnings, endings, and scale that felt unsettling. Yet once accepted, expansion became a unifying framework. It explained redshift. It explained the cosmic microwave background. It explained the large-scale distribution of galaxies. James Webb does not overturn this framework. It enriches it. By revealing early structure and detail, Webb challenges how we model expansion's interaction with matter. It suggests that the interplay between growth and stretching may be more nuanced than previously thought. There is also a subtle but important shift in perspective that comes with this. When size is no longer fixed, measuring the universe becomes less about finding a number and more about describing behavior. How fast does space stretch at different times? How does that stretching influence structure? How does structure feed back into expansion through gravity? These questions replace the simpler notion of cosmic size as a static attribute. For someone listening quietly, this does not require holding equations or timelines in mind. It can be approached more gently. The universe is not a container. It is an evolving system. Its scale changes. Its distances grow. Its structure adapts. James Webb's role is to show us snapshots of this process at stages we could not previously see. Each snapshot reveals a universe at a different size, under different conditions. When those snapshots do not align perfectly with expectations, it does not mean the universe is misbehaving. It means our expectations were incomplete. This incompleteness is where progress happens. As expansion continues, the universe will grow larger. Galaxies will drift farther apart. The observable universe will change. but the light already on its way will continue arriving, carrying information about earlier sizes and states. James Webb catches some of that information, particularly from times when the universe was compact and energetic. The refusal of the universe to stay the same size is not dramatic. It does not announce itself with sudden shifts. It unfolds steadily, governed by equations that describe how energy and geometry interact. Understanding those equations requires data. Webb provides data from an era where expansion, density and structure intersected in ways that still influence what we see today. For a long time, the word expansion carried a single, uncomplicated meaning. Something gets bigger. The distance between its parts increases. That idea works well for rising dough, inflating balloons, or spreading ripples on water. But when astronomers talk about the expansion of the universe, they are pointing to something more subtle, something that resists everyday comparison. It is not just that distances increase, it is that the framework in which distance exists changes, and that change itself evolves over time. Expansion is not constant, it is not uniform across history, and it does not affect everything in the same way. This is where the story becomes more intricate. When the expansion of the universe was first recognized, it was tempting to imagine it as a simple outward motion, galaxies flying away from one another through static space. That picture was quickly abandoned. The mathematics of general relativity made it clear that space itself is dynamic. It stretches, and as it stretches, it carries galaxies with it, not because they are being pushed, but because the distances between stable points in space are increasing. This distinction matters because once space itself becomes active, expansion stops being a single phenomenon and becomes a set of related behaviours. There is expansion, which describes the increase of distance over time. There is the expansion rate, often expressed through the Hubble parameter, which tells us how fast that increase is happening at a given moment. And then there is acceleration, which tells us whether that rate itself is changing. James Webb's observations touch all three, even if indirectly. To understand why acceleration is such a profound complication, it helps to look briefly at expectations. When the universe was discovered to be expanding, the natural assumption was that gravity would gradually slow that expansion. Matter attracts matter. As galaxies move apart, their mutual gravity should resist that motion. Over time, expansion should decelerate. For decades, this was the default assumption. The universe expanded, but it was doing so against a gravitational brake. In the late 1990s, that assumption collapsed. Observations of distant supernovae revealed something unexpected. The expansion of the universe was not slowing down. It was speeding up. The farther away the supernovae were, the faster the expansion appeared to be at the time their light was emitted. This implied that some form of repulsive effect was at work, overpowering gravity on the larger scales. This effect was given a name, dark energy, not because it was understood, but because it was necessary. Acceleration changed everything about how expansion was interpreted. An expanding universe that slows down behaves very differently from one that speeds up. In a decelerating universe, regions that are currently beyond our observational reach might eventually become visible. In an accelerating universe, the opposite happens. Regions that are visible now may eventually disappear beyond the cosmic horizon, their light stretched and diluted until it can no longer reach us. James Webb does not directly measure acceleration, but by observing galaxies at different redshifts, it provides data points that anchor models of how expansion behaved in the past. Those models rely on understanding how different components of the universe influence expansion. Matter, both ordinary and dark, tends to slow expansion through gravity. Radiation also influences expansion, particularly in the early universe. Dark energy appears to drive acceleration at late times. The balance between these components changes over time. Early in cosmic history, radiation dominated. The universe was hot and dense. expansion slowed rapidly. As the universe cooled, matter took over as the dominant influence. Expansion continued to slow, but more gently. Eventually, as matter became diluted by expansion, dark energy began to dominate, and expansion started accelerating. This sequence is not arbitrary. It follows from equations that relate energy density to geometry. But the exact timing and strength of these transitions depend on parameters that must be measured. James Webb observes the universe during the matter-dominated era, before dark energy became dominant. This makes its data especially valuable. It probes a time when expansion was slowing, allowing structures to form efficiently. This context helps explain why early galaxies might appear more developed than expected. Slower expansion means gravity had more opportunity to pull matter together. Higher densities mean cooling could proceed faster. The conditions were favourable for rapid growth. But this does not fully resolve the tension. The rate at which Webb's observed galaxies appear to have formed still challenges standard timelines. This is where acceleration enters indirectly. Because the current accelerated expansion affects how we interpret distances and redshifts, it also affects how we reconstruct earlier expansion behaviour. Distance estimates rely on integrating expansion rate over time. If acceleration behaves slightly differently than assumed, those integrals change. Small changes compound over billions of years. This is why expansion, acceleration and stretching cannot be treated separately. They are aspects of the same evolving process. The phrase "stretching of everything" needs careful handling here. Expansion stretches space, not objects. Galaxies do not grow larger because of expansion. Atoms do not expand. Even galaxy clusters remain gravitationally bound. What stretches is the distance between objects that are not bound together. This selective stretching leads to a universe that feels paradoxical. On small scales, nothing seems to change. On large scales, everything drifts apart. James Webb's observations sit precisely at the interface between these scales. It observes individual galaxies, which are bound systems, but it places them within a backdrop of expanding space that affects their separation, their apparent brightness, and their observed wavelengths. When light travels through expanding space, it stretches. Its wavelength increases. This stretching is redshift. Redshift is not just a Doppler effect. It is a record of expansion imprinted on light itself. The amount of stretching encodes information about how much the universe expanded during the light's journey. This is why redshift is such a powerful tool. It ties observation directly to cosmic history. James Webb measures redshift with high precision. By doing so, it captures how much stretching occurred between emission and observation. But interpreting that stretching requires knowing how expansion rate changed during that interval. This is where acceleration complicates the picture. If expansion rate were constant, redshift would translate straightforwardly into distance and time. But because expansion rate changes, redshift reflects an integrated history rather than a single value. Think of it like measuring the length of a road while the road itself is being extended as you walk along it. The distance you travel does not correspond neatly to how far away the destination is at the moment you arrive. This analogy breaks down at some point, but it captures the core difficulty. James Webb's data pushes into regimes where this difficulty becomes dominant rather than marginal. The stretching of space also affects how we think about the future. In an accelerating universe, expansion will continue to speed up. Distant galaxies will recede faster and faster. Eventually, only gravitationally bound systems will remain visible. Everything else will slip beyond the horizon. This does not affect Webb's observations directly, but it frames their significance. Webb is observing a universe that is more connected than it will be in the far future. Light from distant regions still reaches us. Structures are still visible across vast distances. This connectivity is temporary. Understanding expansion and acceleration helps explain why measuring the universe now is different from measuring it later. The observable universe is not static. It grows, but it also changes character. James Webb provides a snapshot of this process at a critical stage. It shows us a universe where expansion had slowed enough for complexity to arise, but not yet accelerated enough to isolate regions completely. This timing matters. Another subtle effect of expansion is its influence on density. As the universe expands, matter becomes more spread out. Density decreases. This affects star formation rates, galaxy interactions, and the growth of large-scale structure. Webb's observations of early galaxies occur at a time when densities were higher. This helps explain why star formation rates were higher early on. It also means that processes that are rare today were common then. Understanding this helps contextualize Webb's findings. Early galaxies are not simply modern galaxies seen at earlier times. They are products of different conditions. Expansion sets those conditions. Acceleration, meanwhile, determines how long those conditions persist. The earlier dark energy became dominant, the sooner expansion would accelerate, cutting off further growth. The later it became dominant, the longer structure formation could continue. Current models place the onset of dark energy dominance relatively late, several billion years after the first galaxies formed. Webb's observations are consistent with this timeline, but they refine its details. There is ongoing debate about whether dark energy is constant or evolving. If it evolves, then expansion history may differ subtly from standard models. Webb's data could eventually help constrain this by anchoring early structure formation more precisely. This is where expansion and acceleration connect back to the question of size. The size of the observable universe depends on how expansion and acceleration interplay over time. A universe that accelerates strongly limits what can be observed. A universe that accelerates weakly allows more light to arrive. James Webb's ability to see far back suggests that a great deal of structure formed before acceleration became dominant. This supports the idea that the observable universe is richly populated throughout much of its volume. But the stretching of everything means that what we see is always outdated. Light from distant galaxies tells us about a universe that was smaller, denser, and slower in its expansion. The universe now is larger, emptier, and accelerating. This temporal mismatch is unavoidable. James Webb does not resolve it. It makes it explicit. As observations continue, astronomers refine models of expansion, acceleration, and structure growth. Each refinement narrows uncertainties. Each narrows the range of possible cosmic histories. What remains is a picture of a universe that is not static, not uniform in time, and not content to stay the same size. Its scale evolves, its behaviour changes, its future diverges from its past. The universe stretches. It does so at different rates at different times. That stretching shapes everything we observe. James Webb allows us to see how that stretching played out when the universe was young. In doing so, it complicates simple stories but enriches the larger one. Beyond a certain distance, the universe stops behaving like an open landscape and starts acting more like a shoreline. You can see across the water, you can watch waves arrive, but there is a point past which nothing reaches you anymore, no matter how long you wait. This is not because there is a wall or an edge, but because the rules governing motion, light, and expansion quietly impose limits. Astronomers call this boundary the cosmic horizon, and until very recently, it was something discussed mostly in equations and diagrams rather than explored directly. James Webb changed that by bringing the horizon out of abstraction and into observation. The cosmic horizon is often misunderstood as the edge of the universe. It is not. It is the edge of what can ever be observed from a particular location. That distinction is crucial. The universe may extend far beyond this horizon, possibly infinitely so. But information from beyond it cannot reach us, either because it has not had enough time or because accelerating expansion will forever prevent it from arriving. What James Webb revealed is not the horizon itself, but how full and complex the region near it actually is. To understand why this matters, it helps to clarify what kinds of horizons exist in cosmology, because there is more than one, and each plays a different role. There is the particle horizon, which marks the maximum distance from which light has reached us since the beginning of the universe. There is the event horizon, which marks the maximum distance from which light emitted now will ever reach us in the future. And there is the observable universe, which is shaped by the particle horizon but interpreted through expansion. Before Webb, the cosmic horizon was known primarily through indirect evidence. The cosmic microwave background marks the surface from which the earliest light we can see was emitted. That surface lies at an enormous redshift and represents a time when the universe became transparent. Beyond it, light could not travel freely. But galaxies, stars, and structure form after that point. And the question had always been how close to the horizon complex structure could exist. James Webb began answering that question by observing galaxies at extreme redshifts, closer to the horizon than ever before. What it found was not emptiness. It found activity. The expectation had been that regions near the cosmic horizon would be sparsely populated, dominated by small, faint, primitive objects. This expectation was partly shaped by limitations of earlier telescopes. If you cannot see faint structure, it is easy to assume it is not there. Webb removed that limitation. By detecting infrared light stretched by expansion, Webb revealed that the region near the observable boundary is not a quiet fade into nothingness. It is populated by galaxies that are forming stars, interacting and contributing to the universe's large-scale structure. This has profound implications for how the cosmic horizon is understood. The horizon is not a cliff. It is not a sharp cut-off where complexity suddenly disappears. It is a gradual boundary imposed by time and expansion. And near that boundary, the universe is still doing what it does everywhere else, building structure under the influence of gravity. One of the most striking aspects of Webb's observations is how early this structure appears relative to the horizon. Some of the galaxies it has detected formed when the universe was only a few 100 million years old. Their light has been travelling almost the entire age of the universe to reach us. That means these galaxies are not just distant, they are close, in a temporal sense, to the limits of observation. This proximity allows astronomers to test assumptions about how the horizon evolved. The particle horizon grows over time as light arrives from farther regions. Early on, it was small. As time passed, it expanded. But expansion rate influences how quickly this growth happens. Webb's data suggests that by the time the first galaxies formed, the observable region already contained a surprising amount of structure. This implies that the universe became transparent, cooled, and organized quickly enough to allow complexity to arise well within the observable boundary. This observation does not push the horizon outward. It fills it in. That filling has consequences for cosmological models. Many models assume that the universe is homogeneous and isotropic on large scales. This assumption is tested by examining structure across the observable volume. Webb extends that test closer to the horizon than ever before. So far, the evidence suggests remarkable consistency. The properties of galaxies near the horizon resemble those of galaxies at slightly lower redshifts, adjusted for age and environment. This supports the idea that the observable universe is representative of the whole, at least statistically. But consistency does not mean simplicity. The cosmic horizon is shaped not only by the universe's age, but by its expansion history. Accelerated expansion introduces an event horizon that limits future observability. Even if the universe exists beyond a certain distance, light emitted now from those regions will never reach us. James Webb's observations occur in a universe that has not yet fully succumbed to this isolation. Light from very distant regions is still arriving, but understanding what Webb sees requires recognizing that this window is not permanent. This realization reframes the importance of Webb's data. It is not just about seeing farther, it is about seeing before access diminishes. The cosmic horizon also influences how astronomers interpret the size of the universe. The observable universe has a well-defined size based on the particle horizon, but the total universe may be much larger, or it may be infinite. The horizon does not tell us which is true. What it does tell us is how much of the universe can affect us and be affected by us. James Webb's contribution here is indirect but powerful. By mapping structure near the horizon, it helps determine whether there are signs of curvature or repetition that might indicate a finite universe. So far, no such signs have appeared. This absence pushes lower bounds on the universe's size upward. The universe must be at least large enough that the observable region does not wrap around or intersect itself in detectable ways. Webb's deep field observations are especially important for this reason. By surveying small patches of sky in great depth, Webb samples distant regions with high sensitivity. If the universe was small enough to repeat patterns, those repetitions might appear in such surveys. They have not. Another way Webb informs our understanding of the horizon is through rayonization. The early universe underwent a transition from opaque to transparent as the first stars and galaxies ionized surrounding hydrogen. This process left imprints on the distribution of light and matter. By observing galaxies near the horizon, Webb helps trace how reionization progressed across space and time. This progression is tied to how quickly light could travel and how regions became causally connected. If reionization occurred unevenly or later than expected, it could influence horizon estimates. Webb's data suggests that reionization was well underway by the time many early galaxies formed. This again points to a universe that became complex quickly. There is also the question of how sharp the horizon appears observationally. In theory, the particle horizon is a smooth boundary. In practice, observations approach it asymptotically. Signal to noise decreases. Objects become harder to detect. Webb extends this asymptote outward. It does not reveal a sudden cut-off. It reveals diminishing brightness and increasing uncertainty. This gradual fade reinforces the idea that the horizon is not a physical edge. This has philosophical implications as well, though they need not be framed abstractly. The cosmic horizon defines what questions can be answered observationally. Beyond it, speculation replaces evidence. James Webb pushes the boundary between those two domains. By doing so, it also clarifies what cannot be learned through observation alone. No matter how powerful a telescope becomes, it cannot see beyond the horizon imposed by cosmic expansion and finite age. There are limits built into the structure of space-time itself. This does not make observation futile, it makes it precise. Knowing where limits lie helps focus inquiry. It tells astronomers where to stop asking observational questions and start asking theoretical ones. The horizon also affects how we think about causality. Regions beyond the event horizon cannot influence us. Events there are forever disconnected from our future. This separation grows as acceleration continues. James Webb's observations remind us that we are living at a time when much of the universe is still visible. This visibility is not guaranteed forever. The galaxies Webb sees near the horizon are sending us light that left them long ago. That light is a record of conditions that no longer exist. In the future, light from equally distant regions emitted today may never arrive. This asymmetry between past and future is a consequence of accelerated expansion. Understanding the cosmic horizon requires integrating expansion, acceleration, and observation into a single picture. Webb does not solve this integration, but it supplies crucial data points. It shows that the observable universe is richly structured almost all the way out to its limits. It shows that early galaxies existed close to the horizon. It shows that complexity is not confined to nearby regions. This challenges any lingering intuition that the universe fades into simplicity at great distances. For someone listening quietly, perhaps resting, this does not need to feel unsettling. It can be taken as a reminder that limits do not imply emptiness. They imply perspective. The cosmic horizon is not a boundary of existence. It is a boundary of access. James Webb reveals what lies just inside that boundary, and what it reveals is a universe busy with formation, interaction, and growth. As this exploration continues, the natural next question is whether this boundary corresponds to anything physical at all, or whether the universe extends endlessly beyond it in ways that can never be observed. Imagine trying to walk toward the end of a shadow. No matter how far you go, it seems to slip ahead, reshaping itself relative to where you stand. The idea of an edge in the universe works in a similar way. It feels intuitive to assume that something so large must eventually stop somewhere, that there must be a final boundary where space runs out. Yet the deeper astronomy looks, especially with instruments like James Webb, the more that intuition quietly dissolves. The notion of an edge is deeply human. Every object we interact with has limits. Rooms have walls, oceans meet land. Even the sky, to the naked eye, appears like a dome with a surface. For most of history, it was natural to imagine the universe as something contained, perhaps vast, but ultimately finite in a way that could be visualized. Modern cosmology has steadily eroded that picture, not by dramatic contradiction, but by removing the need for an edge altogether. When astronomers talk about the universe today, they are not usually asking where it ends. They are asking how it behaves. Geometry replaces boundary. Expansion replaces enclosure. And observation replaces direct exploration. James Webb plays a subtle role in this shift. It does not show us an edge. It shows us how unnecessary the idea of an edge has become. To understand why, it helps to be precise about what people usually mean when they imagine an edge of the universe. Often they picture a boundary in space, a place where you could, in principle, arrive, a cosmic wall, a final location beyond which there is nothing. This picture is understandable, but it does not align with how space behaves according to our best theories. In general relativity, space is not something that sits inside a container. It is the container. Or more accurately, it is the thing being described. Asking where space ends is like asking where the surface of the Earth ends if you walk in a straight line. You do not encounter a cliff. You eventually return to where you started, even though the surface is finite. This analogy points to one possibility for the universe. It could be finite but unbounded. It could have a total volume but no edges, no special locations where the rules change. Another possibility is that the universe is infinite. Space could extend endlessly in all directions. In that case, there is no edge to reach, not even in principle. Both possibilities are consistent with current observations. What James Webb adds to this discussion is not a definitive answer, but a sharpening of constraints. By observing galaxies near the limits of what can be seen, Webb helps determine whether there are signs that space curves back on itself or repeats. So far, none have been found. If the universe was small enough and curved enough, light travelling long distances might wrap around and produce repeating patterns. The same galaxy could appear in multiple directions. The cosmic microwave background might show correlated features. Extensive searches have found no convincing evidence of such effects. This does not prove infinity. It tells us that if the universe is finite, it is extremely large. Larger than the observable universe by a wide margin. This distinction matters because it reframes the idea of an edge. Even if the universe is finite, its edge is not something we could ever approach, because it does not exist as a location. The only edges we encounter in cosmology are observational. These edges arise not because space ends, but because information cannot travel infinitely fast and because expansion changes what information can reach us. This brings us back to horizons. The particle horizon marks how far we can see into the past. The event horizon marks how far into space events can ever influence us. These horizons behave like edges in practice, but not in substance. They are limits of access, not limits of existence. James Webb's observations near these horizons show us something important. They show that approaching an observational edge does not reveal emptiness or breakdown. It reveals more universe, behaving according to the same principles as everywhere else. This is why the idea of an edge becomes increasingly unsatisfying the more data we gather. If there were a true spatial edge nearby, we might expect to see anomalies as we approach it. Distortions, changes in physical laws, a thinning out of structure. Webb sees none of that. Instead, it sees galaxies forming, interacting and evolving right up to the limits of observability. This consistency supports the cosmological principle, the idea that the universe is roughly the same everywhere on large scales. An edge would violate that principle by introducing a special location. So far, observations do not require such a violation. Another reason we may never reach an edge is expansion itself. Even if the universe had a finite extent with an edge somewhere, expansion would make that edge recede from us. Not because it is moving through space, but because the space between us and it would be growing. Depending on the rate of expansion, the edge could remain forever out of reach. In an accelerating universe, this effect becomes absolute. Regions beyond the event horizon cannot be reached or influenced, no matter how long we wait or how fast we travel, because space itself expands too quickly. James Webb operates entirely within this expanding framework. It observes light that has travelled for billions of years, but it does so knowing that some regions of the universe are already beyond future reach. This introduces a subtle asymmetry. We can see farther into the past than we can ever interact with in the future. The idea of reaching an edge implies travel. It implies motion through space. But cosmological expansion undermines this implication. On large scales, motion through space is not enough. Space itself changes faster than travel can compensate. Even travelling at the speed of light does not guarantee reaching distant regions if expansion accelerates sufficiently. This is not science fiction. It is a consequence of the equations describing space-time. James Webb's observations bring this consequence into focus by showing how much of the universe is already near these limits. Another aspect of the edge question involves the topology of the universe. Topology describes how space is connected globally. A universe can be finite without edges if its topology loops back on itself. There are many possible topologies consistent with flat geometry. Some of these topologies would produce detectable signatures, such as repeating patterns in galaxy distributions or the cosmic microwave background. Webb's deep surveys help extend the scale at which such patterns can be searched for. So far, nothing definitive has emerged. This absence again pushes any possible edge farther away. There is also a psychological element to the edge idea. Humans are comfortable with boundaries. They help organize understanding. An edge feels like closure. Without it, the universe can feel unbounded in a way that is difficult to picture. But cosmology does not require pictures that feel comfortable. It requires descriptions that fit observations. James Webb does not offer comforting closure. It offers clarity. That clarity tells us that the universe does not announce an edge within the observable domain. It behaves consistently across enormous distances. Its laws appear stable. Its structure persists. This suggests that if an edge exists, it is either far beyond what we can see or not meaningful in the way we imagine. Another reason we may never reach an edge is that reaching it may not be a well-defined concept. If space is infinite, there is no destination. If space is finite but unbounded, travel eventually returns you to where you started without encountering a boundary. In both cases, the notion of arrival loses meaning. What remains meaningful is observation. James Webb excels at observation, not travel. It gathers information passively, waiting for light to arrive. That light carries evidence about how space behaves, not where it ends. From this evidence, astronomers infer global properties. They do not seek edges directly. They test models against data. So far, the data does not require an edge. This does not mean the universe is infinite. It means that infinity is a simpler explanation than finiteness, with special boundaries, given current evidence. This simplicity is not aesthetic. It is methodological. Models that do not require additional features are preferred until evidence demands otherwise. James Webb has not demanded otherwise. Instead, It has shown that even near the limits of observation, the universe remains busy, structured, and governed by the same physical principles as closer regions. This consistency undermines the motivation for introducing edges. The universe does not need an edge to be meaningful. It does not need a final wall to be complete. Its behaviour is what matters, not its enclosure. The fact that we may never reach an edge is not a failure of exploration. It is a feature of the kind of thing the universe is. James Webb reminds us that understanding does not always come from arriving somewhere. It comes from noticing patterns, constraints, and consistencies. Whether the universe has a definite size or extends without limit is one of those questions that seems simple on the surface and becomes more elusive the longer you sit with it. It sounds like the kind of thing that should have a yes or no answer, a box to tick once the right measurement is made. And yet, after more than a century of modern cosmology, the most honest answer remains conditional. The universe may be finite, it may be infinite, or it may behave in a way that makes those categories feel incomplete. James Webb does not resolve this question, but it sharpens it. And sharpening a question is often the most important step toward understanding what kind of answers are even possible. To begin untangling this, it helps to separate three ideas that are often blended together in casual conversation: finiteness, infinity, and boundedness. These are not the same thing, even though they are frequently treated as if they were. A finite universe is one with a total volume that is limited. An infinite universe has no such limit. A bounded universe has edges or borders. An unbounded universe does not. It is entirely possible for a universe to be finite and unbounded at the same time. That idea feels counterintuitive at first, but it is mathematically consistent and physically plausible. The classic analogy is the surface of the Earth. The surface has a finite area. You could, in principle, calculate how many square kilometres it contains, and yet, if you walk in a straight line on that surface, you never encounter an edge. You do not fall off. You simply continue and eventually return to your starting point. The surface is finite, but unbounded. Cosmology allows for similar possibilities in 3 dimensions. If the universe has positive curvature, it could be finite in volume while lacking any boundaries. Space would curve back on itself. There would be no special locations, no edges where laws change. Every point would be equivalent. Alternatively, if the universe has 0 curvature, it could be flat. A flat universe can be finite or infinite depending on its topology. And if it has negative curvature, it is typically infinite. So the question of whether the universe is finite or infinite depends on both geometry and topology. Geometry tells us how space curves locally. Topology tells us how space is connected globally. James Webb contributes to this discussion by helping astronomers test geometry and topology observationally, even if indirectly. The strongest evidence about cosmic geometry comes from the cosmic microwave background. Measurements of temperature fluctuations in this ancient radiation indicate that the universe is very close to geometrically flat. Not exactly flat in an absolute sense, but flat within the limits of measurement. This result has held up across multiple missions and analyses. A flat universe leaves both finiteness and infinity on the table. Geometry alone does not decide. Topology then becomes the deciding factor. A flat universe could still be finite if it wraps around in specific ways, forming a 3-dimensional analogue of a torus or some more complex shape. In such a universe, travelling far enough in one direction would eventually bring you back to where you started. If that were the case, there could be observational signatures. Light could travel around the universe multiple times. The same structures could appear in different directions. Patterns could repeat. Astronomers have searched for these signatures extensively. They have compared maps of the cosmic microwave background. They have looked for repeating galaxy distributions. So far, no convincing evidence has emerged. James Webb extends these searches into later cosmic times by mapping galaxies near the limits of observability. Its data strengthens the conclusion that if the universe is finite with a non-trivial topology, it must be extremely large, much larger than the observable universe. At this point, infinity becomes the simpler explanation, not because infinity feels intuitive, but because it requires fewer assumptions. However, there is a third possibility that complicates the picture further. The universe may be finite or infinite in ways that do not map cleanly onto classical intuition at all. This is where the phrase, "something stranger," becomes relevant. Modern cosmology is built on general relativity, which treats space-time as a smooth geometric object, but there are strong reasons to believe that this description breaks down at very small scales or very high energies. Quantum gravity, whatever its final form turns out to be, may alter how space and time behave fundamentally. In some approaches to quantum gravity, space is not continuous. It is composed of discrete elements. In others, space-time emerges from more fundamental relationships rather than existing as a basic ingredient. In still others, multiple dimensions beyond the familiar three may play a role. In such frameworks, asking whether the universe is finite or infinite may be like asking whether a number system is long or short. The question itself may depend on the level of description. James Webb does not probe quantum gravity directly, but it does probe regimes where classical descriptions are pushed hard. By revealing early structure near the limits of observation, Webb forces cosmologists to confront whether existing models are sufficient. Another strange possibility arises from inflation, the rapid expansion thought to have occurred very early in the universe's history. Inflation explains several puzzling features of the universe, including its large-scale uniformity and flatness. Some versions of inflation predict that it did not happen just once and stop everywhere. Instead, inflation may continue in different regions, producing a multiverse of expanding pockets. In this picture, our observable universe is one region among many. In such a scenario, the universe as a whole could be vastly larger than what we can observe, possibly infinite. But individual regions like ours would have finite observable volumes. James Webb's observations are entirely contained within our region. They do not confirm or refute the multiverse idea, but by refining measurements of early structure, they help test predictions of inflation models, some of which are tied to whether inflation was finite or eternal. This adds another layer of strangeness. The universe we observe may be finite in practice, infinite in theory, and embedded in a larger structure that defies simple categorization. Even without invoking inflation, there is the issue of observability. The observable universe has a finite size. That is not in dispute. We can calculate it. We can measure it. It grows over time as light arrives from farther regions, but the observable universe is not the universe. It is a sample. The assumption that this sample is representative of the whole is called the cosmological principle. It has served cosmology well, but it remains an assumption. James Webb tests it by looking for deviations at great distances. So far, the assumption holds. The universe looks statistically similar in different directions and at different locations when averaged over large scales. This consistency supports extrapolation. It allows astronomers to reason about the unobservable based on the observable, but extrapolation has limits. Another strange possibility is that the universe has a finite age but infinite spatial extent. This is allowed by general relativity. Space could have been infinite from the beginning, with expansion stretching it further. In this case, there is no moment when the universe was small in total size, even though regions were denser. This challenges the intuitive picture of a tiny universe expanding into a larger one. James Webb's observations of early galaxies do not distinguish between these possibilities directly, but they remind us that early does not necessarily mean small in a global sense. The universe could have been infinite even when it was young. There is also the question of whether infinity is physically meaningful or merely a mathematical idealization. Some physicists argue that infinities signal breakdowns in theory, rather than real features of nature. Others accept them as legitimate descriptions. This debate extends beyond cosmology. It appears in discussions of black holes, quantum fields, and space-time singularities. James Webb does not settle this debate, but by providing data that challenges simple narratives, it keeps the debate grounded in observation rather than speculation alone. The phrase "something stranger" can also refer to the possibility that space has properties we do not yet understand. For example, space could have a finite information capacity. There may be limits to how much information can be stored in a given region. This idea appears in holographic theories, which suggest that the information content of a volume is proportional to its surface area rather than its volume. If such ideas are correct, then the universe could be finite in information content even if it is infinite in extent. This is a different kind of finiteness altogether. James Webb's data, by probing the complexity of early galaxies, indirectly touches on information content. The richness of structure at early times speaks to how quickly information was encoded into matter and radiation. This does not answer the question, but it reframes it. Another angle comes from thermodynamics. An infinite universe raises questions about entropy and equilibrium. In an infinite system, defining global thermodynamic states becomes problematic. Some physicists prefer finite universes for this reason. Others argue that thermodynamics applies locally and does not require global finiteness. Again, observation does not force a choice yet. What James Webb has done is eliminate some of the simpler options. It has shown that the universe is not small in any meaningful sense. It has shown that structure exists almost all the way to the observational limits. It has shown that early complexity was not confined to a narrow region. These results push any possible finiteness far beyond what we can currently access. At the same time, Webb has not revealed any repeating patterns or anomalies that would demand exotic topology within the observable region. So where does that leave us? It leaves us with a universe that behaves as if it were infinite on the scales we can test. It leaves open the possibility that it is finite but unimaginably large. And it leaves room for deeper theories that may redefine what size even means. This does not need to feel unresolved in a frustrating way. It can be accepted as a reflection of how science progresses. Some questions are refined long before they're answered. Some answers change the meaning of the question itself. James Webb's role is not to declare whether the universe is finite or infinite. Its role is to show us how much of the universe is visible, how structured that visible portion is, and how early complexity emerged. Those facts inform the debate without closing it. From the ground where we stand, it is easy to imagine ourselves as fixed while everything else changes. The Earth feels solid. The sky feels like a backdrop. Even when we accept that the universe is expanding, that acceptance often stays abstract, detached from daily experience. But when the universe gets bigger in a real physical sense, our place within it changes too. Not because we move, but because the context around us stretches and rearranges itself. James Webb does not show us ourselves, it shows us scale. And scale has a way of quietly altering perspective. For most of history, humanity placed itself at the centre of things without much resistance from observation. The Earth felt central because everything seemed to move around it. Even when the Sun replaced Earth as the centre of motion, the broader universe still felt arranged with us in mind. The stars were distant, but they appeared fixed. The cosmos felt large, yet static, like a grand but unmoving stage. That sense of centrality did not survive the discovery of expansion. Once astronomers realized that galaxies were moving away from each other, and that this recession was not centered on any particular location, the idea of a privileged position dissolved. Expansion happens everywhere. From any galaxy, all sufficiently distant galaxies appear to be receding. This is not because there is a center we are near, but because space itself is stretching uniformly. In an expanding universe, every location is locally ordinary. James Webb reinforces this idea in a way earlier telescopes could not. By observing galaxies across a vast range of distances and times, it shows that the processes shaping the universe are not unique to our region. Star formation, galaxy growth, chemical enrichment and structural evolution occur throughout the observable universe, even near its limits. This uniformity has consequences for how we understand our place. When the universe was thought to be static and eternal, place could be imagined as absolute. When the universe began to expand in our understanding, place became relative. And when expansion turned out to be accelerating, place became temporary in a deeper sense. Our location in the universe is not just a position in space. It is a position in time. James Webb's images make this explicit. The galaxies it observes are not just far away. They are earlier. They represent stages of cosmic history that no longer exist locally. Looking at them is not like looking across space. It is like looking across eras. This temporal layering reshapes the idea of place. We do not inhabit the universe as a whole. We inhabit a moment within its evolution. That moment matters. Right now, we live at a time when the universe is old enough to have formed complex structures, heavy elements, and stable planetary systems. It is also young enough that light from distant regions can still reach us. These two conditions do not overlap indefinitely. In the far future, the universe will be larger, emptier, and more isolated. Many galaxies we can see today will no longer be observable. Their light will be stretched beyond detectability. From any given location, the visible universe will shrink. James Webb shows us the universe before this isolation fully sets in. This timing gives our place a particular character. We exist at a moment when the universe is both expansive and connected. We can see far back. We can reconstruct cosmic history. We can map structure across enormous scales. This is not guaranteed forever. Understanding this does not require sentimentality. It is a straightforward consequence of expansion and acceleration. As dark energy drives accelerated expansion, horizons tighten, regions fall out of causal contact, information becomes inaccessible. From a future vantage point, the universe will appear smaller, not because it has shrunk, but because access has narrowed. Our place, therefore, is defined not only by coordinates, but by opportunity. James Webb capitalizes on that opportunity by observing a universe still rich in accessible information. It allows us to see early galaxies, to trace how matter assembled, and to understand how cosmic conditions evolved. This capability shapes how we interpret our location. We are not central in space. We are not privileged in geometry. But we are situated at a time when understanding is possible at a depth that may not always be available. There is another way in which the universe getting bigger alters our sense of place. As distances increase, familiar reference points lose relevance. The Milky Way becomes just one galaxy among hundreds of billions. Local clusters become small nodes in a vast network. James Webb's deep field images make this visually unavoidable. In a patch of sky that appears empty to the naked eye, Webb reveals thousands of galaxies, each containing billions of stars. None of these galaxies is marked as special. None is highlighted as central. The effect is cumulative. Scale erodes hierarchy. This erosion does not diminish significance, it reframes it. Our place is not important because of where it sits in a cosmic map. It is important because of what it enables. We occupy a location where matter has organized itself into forms capable of observing, modeling, and questioning the universe. That capability is local, not universal. Most regions of the universe are inhospitable to life as we know it. Even fewer support observers. James Webb does not search for meaning. It reveals conditions. From those conditions, implications follow. One implication is that our place is shaped by cosmic history. The elements that make up our bodies were forged in stars. Those stars formed in galaxies. Those galaxies assembled under conditions set by expansion, density, and time. By observing early galaxies, Webb shows us earlier versions of the environments that eventually made our existence possible. This does not imply inevitability. It implies contingency. If expansion had proceeded differently, if structure had formed more slowly, if dark energy had dominated earlier, the universe might still exist, but our place within it might not. So when the universe gets bigger, our place becomes less about location and more about context. Context includes physical conditions, timing, and connectivity. Connectivity is particularly important. Right now we are connected to a vast region of the universe through light. We receive information from billions of years ago and billions of light years away. That information shapes our models and expectations. James Webb extends that connectivity farther than before. It shows us regions near the observational horizon, still connected to us through ancient light. This connection is fragile. As acceleration continues, future observers will have access to less information. Their place will feel more isolated, not because they moved, but because the universe expanded beyond their reach. In that sense, our place is defined by a narrowing window. This does not make it special in a mystical way. It makes it specific in a physical way. Another subtle shift in perspective comes from realizing that expansion does not move us away from the center, because there is no center to move away from. Every point experiences expansion the same way on large scales. This symmetry means that our place is not privileged by geometry. It is ordinary. James Webb's observations support this ordinariness. The physics governing early galaxies appears consistent across directions. There is no evidence that our region is special or unusual. This ordinariness is one of the most robust results in cosmology. At the same time, the fact that we can observe ordinariness across such vast scales is itself remarkable. It suggests that the universe is comprehensible, that laws discovered locally apply elsewhere, that models built from nearby observations can be extended outward. James Webb tests this assumption by observing distant regions under very different conditions. So far, the assumption holds. This consistency allows us to situate ourselves confidently. We are not guessing blindly about the universe. We are extrapolating carefully from evidence. Our place, then, is not one of dominance or centrality. It is one of participation. We participate in the universe by observing it, by measuring it, by refining our understanding of how it behaves. As the universe gets bigger, that participation does not scale with size. We do not become smaller in relevance because the universe is larger. Relevance is not measured in meters. Instead, relevance is tied to interaction, to observation, to comprehension. James Webb expands the range of interaction. It brings distant epochs into conceptual proximity. It allows us to compare early and late stages of cosmic evolution. This comparison reshapes how we think about our place in time. We are not early in the universe's history. Billions of years preceded us. We are also not at the end. Billions of years will follow. But we occupy a middle era, one where stars are common, galaxies are active, and heavy elements are abundant. This middle era may be uniquely favourable for complexity. The universe getting bigger does not erase that fact. It contextualizes it. There is also a quieter implication. As expansion continues, the night sky will change. Over extremely long timescales, distant galaxies will fade. The universe will appear emptier from any given vantage point. Future observers may not be able to infer expansion or cosmic history as easily as we can. The evidence will be gone. James Webb's data preserves some of that evidence. It records snapshots of a universe still visible across vast scales. In doing so, it anchors our place historically. We are observers at a time when the universe is open to observation. This openness is not permanent. Understanding this does not require anxiety. It is simply part of how physical systems evolve. Our place is temporary, but not insignificant. James Webb does not tell us where we belong. It tells us what surrounds us, how it formed, and how it changes. From that, a picture of place emerges. It is a place without a centre, a place defined by expansion, a place shaped by timing. As the universe gets bigger, our place does not shrink in meaning. It becomes clearer in context. Strangely enough, learning how large the universe is does not alter the way gravity pulls objects together, does not change the path of light, and does not shift the orbit of a single planet. Stars continue to burn. Galaxies continue to drift. Physics carries on exactly as it did before the measurement was made. In that sense, knowing the size of the universe changes nothing at all. And yet, at the same time, it changes almost everything about how those facts are understood, connected, and interpreted. This dual effect sits at the heart of why questions about cosmic size persist, even when they appear impractical. From a strictly physical perspective, the universe does not behave differently because we know more about it. Its expansion rate does not adjust to our measurements. Its geometry does not flatten or curve in response to observation. Whether the universe is finite, infinite, or something more subtle, the underlying processes continue uninterrupted. Hydrogen fuses into helium. Supernovae scatter heavy elements. Space expands according to its governing equations. Nothing reacts to our awareness, but knowledge does not exist for the universe. It exists for us. And this is where everything begins to shift. Before astronomers had any sense of the universe's scale, human understanding was locally constrained. The sky appeared vast but shallow. The stars were distant lights, not entire galaxies. The universe was big, but not incomprehensibly so. That picture shaped philosophy, religion, and even science itself. Questions about origins, purpose, and structure were framed within a relatively small imagined cosmos. As measurements improved, that imagined cosmos grew, and with each expansion of scale, assumptions that once felt solid began to loosen. James Webb represents the latest and most dramatic step in that process so far. By revealing galaxies near the observational limits, by showing complexity where simplicity was expected, Webb does not just add distance to our maps. It stretches the conceptual framework those maps sit within. This is where knowing the size of the universe changes everything. When the universe was thought to be static and relatively small, it was easier to imagine humanity as occupying a meaningful centre. When it became larger, that centre dissolved. When it became dynamic and expanding, the idea of a fixed cosmic stage disappeared. When acceleration was discovered, even long-term connectivity became uncertain. Each shift removed a layer of assumed permanence. James Webb accelerates this removal by confronting us with scale directly. Not as an abstract number, but as populated, structured reality, extending almost as far as observation allows. Knowing the size of the universe also changes how scientific questions are prioritized. In a small universe, global questions feel approachable. One might imagine measuring everything, mapping it completely, understanding it in totality. In a universe that is vastly larger than what can ever be observed, that ambition must be replaced with statistical reasoning and inference. Cosmology becomes less about cataloguing everything, and more about understanding patterns, distributions and laws that operate everywhere. James Webb's observations reinforce this approach. No matter how many galaxies it observes, they represent a sample, a rich sample, but still a sample. Conclusions must be drawn carefully, acknowledging that unseen regions exist beyond reach. This recognition changes the nature of explanation. Instead of asking, "What is the universe doing everywhere?" astronomers ask, "What does the universe do under these conditions, and can those conditions be assumed to exist elsewhere?" Knowing the size of the universe also reframes uncertainty. In a small or bounded system, uncertainty can feel temporary. Gather enough data, and the picture will eventually become complete. In an effectively endless universe, uncertainty becomes structural. Some questions may never be resolved observationally, not because of technological limits, but because of fundamental constraints imposed by space-time itself. James Webb makes those constraints visible by approaching the cosmic horizon and revealing that it is filled with structure rather than emptiness. Webb shows that lack of access does not imply lack of content. There is more universe beyond what can be seen, and that more cannot be reached by better instruments alone. This realization forces a distinction between ignorance and inaccessibility. Ignorance can be reduced, inaccessibility cannot. Knowing the size of the universe helps clarify which category a question falls into. For example, questions about the geometry of space can be constrained by observation. Questions about what lies beyond the event horizon cannot. No amount of improved resolution will change that. This distinction changes how science is practiced. It encourages humility without discouraging inquiry. On a more practical level, knowing the size of the universe changes how observations are interpreted. Brightness, mass and distance are all intertwined. In a larger universe, objects can appear similar while being fundamentally different. A bright galaxy might be intrinsically luminous or merely closer than assumed. A faint object might be small or simply distant. James Webb's data forces astronomers to confront these ambiguities directly. Models must account for a wider range of possibilities. Error bars widen before they narrow. This is not a setback, it is a refinement. Knowing the size of the universe also changes how early cosmic history is understood. In a smaller imagined universe, early structure formation must happen quickly and locally. In a vast universe, multiple regions can evolve in parallel. Rare events become statistically inevitable somewhere. What looks unusual locally may be commonplace globally. This matters when interpreting Webb's early galaxy discoveries. Galaxies that appear surprisingly massive early on may not indicate that all galaxies formed that way. They may represent the early tale of a broad distribution in a very large universe. Scale changes expectation. The larger the universe, the more room there is for variation without violating underlying laws. This perspective reduces the temptation to overinterpret anomalies while still taking them seriously. At the same time, knowing the size of the universe changes nothing about the immediate human experience. The night sky does not look different because we know more about it. The Milky Way remains a faint band to the naked eye. Constellations still appear unchanged. On human timescales, the universe feels static. This disconnect between intellectual understanding and sensory experience is part of what makes cosmology unusual. James Webb's images bridge that gap slightly by providing visual evidence of scale. But even those images must be interpreted. A photograph of thousands of galaxies does not automatically convey their distances, ages, or significance. Understanding scale remains an act of reasoning, not perception. This is why knowing the size of the universe can feel both transformative and irrelevant. Transformative, because it reshapes models, expectations, and philosophical context. Irrelevant, because daily life proceeds unaffected. Both responses are valid. There is also a subtle shift in how causality is understood when the universe is known to be vast. In a small universe, events feel more tightly connected. In a large one, most events are causally isolated. The majority of what happens has no influence on us and never will. This isolation does not diminish importance locally, but it alters the sense of interconnectedness. James Webb's observations reinforce this by showing galaxies whose light left long before Earth existed, and whose future evolution may never influence our region. These galaxies are real, structured, and active, yet permanently disconnected from our future. Knowing this changes how the universe is mentally defined. It becomes less of a single arena and more of a collection of largely independent histories. This does not fragment science, it refines it. Another way, knowing the size of the universe changes everything, is in how finality is approached. In smaller conceptual universes, ultimate answers feel plausible. In larger ones, finality recedes. There is always more beyond current reach, more data that could exist but cannot be accessed. James Webb's success does not close the book on cosmology. It opens new chapters while making it clear that the book has no final page. This openness influences how theories are evaluated. Flexibility becomes a strength. Models are judged by their consistency, predictive power, and ability to accommodate new data, not by claims of completeness. Knowing the size of the universe also changes how beginnings and endings are thought about. If the universe is finite and small, beginnings feel localized. If it is vast or infinite, beginnings may be regional. Inflationary models already suggest that what we call the beginning may be a local feature rather than a global one. James Webb does not observe the beginning itself, but it observes conditions close enough to challenge simplified origin stories. This does not remove the concept of a beginning. It complicates it. Endings are similarly affected. In a vast accelerating universe, endings are not synchronized. Different regions will experience isolation at different times. There is no universal finale. This decentralization of cosmic narrative mirrors the decentralization of place. There is also a cultural effect to knowing the universe's size, though it unfolds slowly. As cosmic scale becomes more widely understood, it seeps into how people think about humanity's significance, fragility, and resilience. This does not lead inevitably to pessimism or awe. It leads to recalibration. James Webb contributes to this recalibration by providing evidence rather than metaphor. Its images are not symbolic. They are data-rich records of structure and distance. From those records, meaning is not imposed. It is inferred cautiously. Knowing the size of the universe changes everything intellectually because it forces precision. Vague statements become untenable. Assumptions must be justified. Language must be careful. Knowing the size of the universe changes nothing physically, because the universe does not respond to being known. Both truths coexist without contradiction. This duality does not need resolution. It can simply be noticed. Understanding scale does not demand emotional response. It offers context. James Webb gives that context sharper edges, clearer bounds, and richer content. It shows that the universe is large enough that no single perspective dominates, yet structured enough that understanding is possible. Slowly, attention returns inward, not because the universe has been exhausted, but because the mind naturally seeks balance after stretching so far outward. After following light across billions of years, after tracing expansion, horizons, and size beyond intuition, there comes a moment where the view widens one last time and then settles, not into conclusions, but into orientation. This is the quiet drift back toward Earth, carrying a larger sky with us than the one we started with. Nothing about the planet has changed during this journey. Its mass is the same. Its orbit is steady. The atmosphere still holds close, thin and protective. Yet perspective has shifted, and perspective has consequences, even when nothing physical moves. James Webb does not point back at Earth. It never turns its mirrors toward home. And still, by looking outward so deeply, it alters how home is understood. Not emotionally, not symbolically, but structurally, as part of a system that extends far beyond any immediate horizon. For most of human existence, the sky functioned as a ceiling. It was something above, not something through. Even once it became clear that stars were distant suns, the sense of enclosure lingered. The universe felt like a large but bounded place, and Earth felt embedded within it, in a way that was difficult to question. That sense does not survive careful measurement. What James Webb reveals, piece by piece, is not just distance, but continuity. The same physical processes operating here operate elsewhere. The same laws apply across enormous scales. The same matter cycles through different forms, whether in a nearby star or a galaxy formed billions of years ago. This continuity stretches the sky open. Instead of a backdrop, it becomes a cross-section. Instead of a roof, it becomes a depth. Instead of something above us, it becomes something we are within. Drifting back to Earth with this understanding does not diminish the planet's importance. It reframes it. Earth is not important because it sits beneath the sky. It is important because it exists at all, as one of countless outcomes of processes that operate across the universe. It is not unique in its basic ingredients. It is specific in their arrangement. James Webb's observations reinforce this specificity by showing how early galaxies formed, how stars ignited, how heavy elements accumulated. Webb outlines the long chain of conditions required for planets like Earth to exist. None of those steps were guaranteed. Each depended on timing, density, expansion rate, and chemistry. Seeing that chain clearly makes Earth less inevitable and more contingent. This contingency changes how scale feels. In a small universe, Earth might feel central. In a large universe, it feels local. Not insignificant, just local. A particular solution to a vast set of possibilities. This is not a demotion, it is a clarification. The larger the sky becomes, the more clearly Earth appears as a place where processes converged in a specific way. Carbon formed in earlier stars, oxygen accumulated, heavy elements were recycled through generations of stellar death and rebirth. Planets condensed around long-lived stars. Chemistry unfolded over long periods without being erased by catastrophic instability. James Webb observes the earlier stages of this story. It sees galaxies assembling. It sees star formation environments unlike our own. It sees conditions that existed long before Earth was possible. By placing Earth within that timeline, our location becomes temporal as much as spatial. We exist after the universe has done a great deal of work, but before it has finished changing. This matters. There is a tendency, when confronted with vastness, to assume insignificance follows automatically. But insignificance is not a physical property. It is an interpretation. The universe does not assign importance. It produces outcomes. Earth is one such outcome. Drifting back to Earth with a larger sky above us means letting go of the need for centrality while retaining relevance. Our planet does not need to be the focus of the universe to matter within it. James Webb's data does not strip meaning away. It removes shortcuts. It shows that meaning cannot be derived from position alone. It must be grounded in interaction, emergence, and persistence. From a physical standpoint, Earth occupies an unremarkable location. It is not near a cosmic centre, because no such centre exists. It is not close to an edge, because edges are observational, not structural. It is not aligned with anything special. And yet, from a structural standpoint, Earth exists at a moment when the universe is transparent, connected, and chemically rich. This coincidence of conditions defines our place more than coordinates ever could. James Webb also reminds us that Earth is not separate from the sky. The distinction between here and out there dissolves under scrutiny. The atoms in our bodies were not made locally. They were assembled elsewhere and delivered through processes spanning billions of years. In that sense, the sky is not above us. It is within us. This is not metaphor, it's composition. The larger the sky becomes in understanding, the harder it is to maintain rigid boundaries between Earth and cosmos. They are part of the same physical narrative, unfolding at different scales and tempos. Drifting back to Earth does not mean retreating from that narrative. It means recognizing where we sit within it. Another effect of carrying a larger sky is how time is perceived. James Webb compresses vast durations into images and data. Billions of years are represented in single frames. Entire epochs appear side by side in comparative plots. Returning to Earth after this kind of temporal compression can make human timescales feel oddly layered. Days still pass, nights still come, but they exist against a backdrop of deep time that does not disappear when attention returns locally. This does not make daily life less real. It makes it more contextualized. The night sky above Earth is no longer just tonight sky. It is a cross-section through history. When a star is visible, its light left long ago. When a galaxy is visible, its light left unimaginably long ago. Even the nearest celestial objects carry delay. James Webb extends this realization far beyond naked eye intuition. It turns delay into structure. It shows that what we see is always a mixture of times. Returning to Earth with this awareness subtly changes orientation. The present moment remains the only place we act, but it is no longer mistaken for a universal now. The universe does not share our present. This does not isolate us. It situates us. Another aspect of this drift back involves limits. James Webb reveals how far observation can reach and where it must stop. It clarifies that there are parts of the universe that will never be seen, no matter how advanced observation becomes. Knowing this does not diminish curiosity. It sharpens it. It separates questions that can be addressed from those that must remain theoretical. It teaches restraint without discouraging exploration. Bringing that restraint back to Earth means accepting that not everything needs resolution to be meaningful. Understanding where limits lie is itself a form of understanding. The sky above Earth, when seen through this lens, becomes less about conquest and more about relation. We do not stand beneath something waiting to be reached. We exist within something that unfolds according to rules we can partially map. James Webb does not invite ambition in the sense of domination. It invites precision. Precision in language, precision in assumption, precision in inference. Carrying a larger sky back to Earth means carrying that precision into how we talk about existence, scale, and place. It discourages exaggerated claims of importance and exaggerated claims of insignificance alike. Earth is neither the centre nor a trivial speck. It is a specific outcome in a large, structured universe. This specificity matters because it grounds inquiry. It allows science to proceed without resorting to mythic framing. James Webb's contribution is not spectacle, it is context. Context does not overwhelm, it informs. As the universe grows larger in our understanding, the temptation to summarize or conclude becomes strong. But the deeper lesson of Webb's observations is that summary is premature. Every answer opens further questions. Every boundary revealed implies others beyond it. Drifting back to Earth is not a return to certainty. It is a return to location with expanded awareness. The sky above does not press down. It opens outward. Another quiet effect of this expanded sky is how isolation is perceived. In a vast universe, Earth might seem alone, but isolation is not measured by distance alone. It is measured by interaction. Earth interacts constantly with the universe, through radiation, through gravity, through cosmic history. James Webb shows that interaction has been continuous for billions of years. Light arrives, information flows, structure influences structure. Even regions that are now causally disconnected were once part of a shared history. This continuity softens the idea of cosmic loneliness without invoking sentiment. Earth is not surrounded by emptiness. It is embedded in a dynamic system whose components are spread across enormous scales. Understanding that does not require emotional framing. It follows directly from observation. As the sky grows larger, Earth's fragility becomes clearer, but so does its resilience. It exists in a universe that has undergone dramatic change and continues to persist. James Webb observes early galaxies surviving intense conditions. It observes star formation under extremes. It observes structure emerging from near uniformity. Earth's existence fits within this broader pattern of persistence. This does not guarantee permanence. Nothing does. But it situates Earth within a universe where complexity is not rare once conditions allow it. Drifting back to Earth with this awareness does not lead to closure. It leads to steadiness. The questions raised by James Webb are not meant to be settled quickly. They are meant to be carried forward, refined, revisited. The sky above us is larger now, not because it grew, but because understanding expanded. And that expansion does not end here. Even as attention settles back into familiar surroundings, the context remains. The universe does not shrink back to a backdrop. It remains active, structured, and ongoing. James Webb continues observing. Data continues arriving. Models continue adjusting. The story does not conclude. It continues quietly, beyond any single perspective. Returning to Earth with a larger sky above us does not mean turning away from the universe. It means knowing that the universe does not need to be chased to be present. It is already here, expressed through light, matter, and time, intersecting briefly with awareness on a small planet in a vast evolving whole. And that awareness, once expanded, does not collapse back to its original size. It stays open, even as rest arrives, allowing the sky to remain large without demanding attention, simply present above and around as the universe continues doing what it has always done, whether observed or not.